Everyone, to the day 7 of the winter school organized by MPCST, IIT Indore, and IIA. So today we have as our first speaker Professor Dipankar Bhattacharya, who is a professor at the Inter-University Center for Astronomy and Astrophysics at Pune. He did his PhD from ISC Bangalore in 1988, and his research interest is in the field of high energy astrophysics, primarily focusing on neutron stars, supernova remnants, and gamma ray burst. He is also seminally involved in the developmental work of the Indian multi-wavelength astronomy mission satellite, AstroSat, and today he will be talking about pulsars in the first lecture of the session. With that, I leave the field to Professor Bhattacharya. Professor Bhattacharya.
Thank you very much. Thanks for the invitation and welcome to all the participants. At the outset, I would like to apologize that you may sometimes hear drilling noise from outside, which is suddenly has started happening an hour ago. I hope it will not be too disturbing. So let me share my screen. All right, I hope everybody can view this. So today we are going to talk about pulsars. As you will see, these are really very interesting objects, which are somewhat unique among all the cosmic objects that we know. So let's start by listening. I hope you can hear this very regular ticks. This is auditory visualization of a radio signal obtained at 410 megahertz using the NRAO 92-meter telescope. So this is recorded from the pulsar called B0329 plus 54 with a period of 0.71 seconds. So what causes these very regular bursts of radio emission that we detect from these objects? So what we understand is bursts of radio emission are seen by us when a rotating, strongly magnetized neutron star with highly collimated radiation beam attached to their magnetic poles point their beams to us once in a rotation period. So as this animation shows, there is a neutron star with a spin axis which is vertical in this diagram and a magnetic axis which is at some angle with respect to it. There are two highly collimated beams which are attached to two poles, and at some point during its rotation, the beam points towards us. At other times, it is pointed away. So when it is pointed towards us, we get the signal. When it is pointed away, we don't see anything. So once in a rotation period, we see a pulse of emission. And that's what causes this regular arrival of pulses. The period of the pulsar is identified as the spin period of the neutron star. So pulsars were discovered in 1967. So this is almost 60 years ago now, maybe 50 plus years ago. Then by a graduate student, Jocelyn Bell, working in this large Cambridge radio telescope array, working at 81.5 megahertz. And she was working for a supervisor, Anthony Huish, we've seen in this picture. This is Jocelyn Bell, this is Anthony Wish, many years later, of course. This is a picture from the time that the pulsars were discovered. And what they saw in their chart recorder was these irregular arrival of bumps in the radio signal, radio intensity. And so this was the first observation of the pulsar, 28th November 1967. And this first pulsar which was discovered was christened Cambridge Pulsar 1919, which is now called PSRB 1919 plus 21. So these numbers are just coordinates in the sky, right ascension and declination. And this pulsar had a period of 1.337 seconds. So from then on, radio observatories have contributed a great deal in pulsars, and a great deal of contribution has been made by very large single-dish radio telescopes. And some of the iconic radio telescopes which have really pushed pulsar astronomy forward are shown here. The 1,000-foot Arecibo telescope was absolutely the mainstay of pulsar astronomy for a very long time. Unfortunately, just a couple of months ago, this telescope collapsed. So now this is no longer in operation. There was a 300-foot Green Bank telescope, which also contributed a lot to pulsar astronomy. This telescope operated from 1962 to 1988, when this one also collapsed. So this has now been replaced by a 100-meter radio telescope. Two telescopes which have been there from the early days and still operating is the 64-meter Parkes radio telescope in Australia and the 76-meter Lovell telescope in Jodrell Bank in the United Kingdom. So these are among many other telescopes which have also contributed greatly to pulsar astronomy, increasing the total number of pulsars discovered today to getting to nearly 3,000, so more than 2,800 now. So over time, we have now discovered pulsars with a whole range of spin periods. You saw the first pulsar, which was about 1 second period, 1.33 second period. Then there are pulsars which have much shorter period. For example, this is one of the iconic pulsars, Crab pulsar, which has all the bells and whistles, so it can be studied in great detail in many aspects. This happens to be within the remnant of a supernova that occurred in 1054 AD. So we have a record of the supernova, we see the remnant of the supernova. The remnant of the supernova is being powered by this pulsar. And the pulsar has a fast spin period of 33.7 milliseconds. So if you do similar audio visualization, then it will sound like this. So you can see that the subsequent pulses are so close together, so you can hardly make out within our persistence of hearing. Over time, one has discovered even much faster pulsars. One of the fastest pulsars we know today is PSRB 1937 plus 214. This was the first pulsar of the millisecond pulsar category that was discovered in 1982. Its period is 1.6 milliseconds. And its audio visualization will actually sound like a tone, like a single frequency musical tone of 642 hertz. So we have this great range of diversity in pulsar spin periods. And let us see what else. So today, if you look at the distribution of spin periods of radio pulsars, you have a large majority of them somewhere around 1 second. So this is logarithm of period. This is 1/3 of a second. This is 1 second. So the peak of the period distribution lies around there. But there is also a secondary bump in this distribution, which happens to be at millisecond period. This is 1 millisecond, this is 3 milliseconds. So there is a distinct population which is seen at much shorter periods. And this population was discovered from 1980s onwards. Until then, existence of this second population was not known. So we'll come to the origin of this population towards the end of this talk. But let us look at the general properties of pulsars to start with. So as we said, these pulsars have mostly been discovered in radio wavelengths, but they are not only active at radio. Pulsars are broadband emitters. Here is an example. As I mentioned, Crab pulsar, we can study it in great detail because of its proximity, brightness. And so this is the Crab pulsar, a single pulse of the Crab pulsar, single period of the Crab pulsar with radio intensity and X-ray intensity plotted as a function of time. So this is within one period. So this is pulse phase going from 0 to 1 means this is the fraction of a period. So this is one full period. So during one period, you see a little bit of blip in radio emission, and then a strong peak of radio emission, and then a weak peak of radio emission. In X-rays, you see a gradual rise of X-ray intensity, almost aligned with the radio peak, and then a drop with some amount of bridge emission, and then the secondary peak also aligned with this second peak in radio, and then it drops off. And the Crab pulsar is now seen all the way from the lowest frequency radio at which you can measure to tera-electron volt gamma rays. It emits at all these wavelengths. So pulsars in general must be very broadband emitters. It has not been possible to detect emission at all wavelengths from all pulsars, partly because of our instrument sensitivity, because some pulsars could be far away, weaker. So it may not be possible to detect each one of them at all frequencies. But it is reasonable to say that the pulsars are broadband emitters with emission all over the electromagnetic band. Now, in Crab pulsar, we saw that the radio profile and the gamma ray profile or the X-ray profile look relatively similar. But this is actually not in general the case. In general, the radio and the high energy pulse profiles are quite different. Here we have shown an example of 6 different pulsars, where red line shows the radio pulse profile and the black line shows the gamma ray pulse profile as measured by the Fermi Gamma Ray Telescope. And you can see that in all these cases, these pulse profiles look very different. And this is actually the norm. The Crab is an exception in terms of the similarity of the two pulse profiles. So what this tells us is that the emission mechanism in the pulsar has quite a bit of complexity, and different emission at different energies probably come from different geometric regions. So we'll see a bit more about that later. Now we talked about the spin period. Now if we look at the spin period and then keep measuring it, we can measure one more quantity of the pulsar fairly easily, and that is the rate of change of spin period. And invariably, all these pulsars that we are talking about, we find that if we follow their spin period over time, they are spinning down. That is, their spin period is lengthening with time, which means the rotational energy, which is there in the pulsar in the form of its spin, is being lost. So the pulsars therefore lose rotational energy and spin down. And the signal that you are receiving, the energy that you are receiving in radiation, comes at the expense of this rotational energy. What I show here is a measurement done by us at X-ray wavelength of the Crab pulsar. What is shown here is the pulse period of the Crab pulsar as measured in these measurements over a period of about 2.5 days. Each of these measurements are half a day apart. And what is plotted in the vertical axis is the change of period in nanoseconds from 33.72067 milliseconds. And you can clearly see there's a very clear measurement of a spin down rate of 36.3 nanoseconds per day. So yes, pulsars do spin down and they do steadily spin down, but the spin down rate is actually very small. So this is Crab pulsar is one of the larger spin down rates. There are many other pulsars which are spin down rates much smaller. So despite the spin down, the pulsars can then be considered as very good clocks. And once the spin down is measured, the spin down can in fact be used also to correct the clock frequency. So using this correction, you can really use pulsars as extremely good clocks. And we will see some applications of that later in this talk. So now that we have two measurements, the spin period and the rate of change of spin period derivative, we can try to look at the distribution of pulsars in these two parameters. And it's a very interesting distribution that you see in this PP dot plane. And on top of which, in this figure is illustrated pulsars of slightly different classification. In blue dots, all the pulsars are shown. Of them, those which are in binary systems are shown in these green dots. Those which have been detected in high energy emission, like optical X-rays or gamma rays, are shown with these red triangles. So you can see that there are regions where largely non-binary pulsars seen mostly at radio wavelengths are present. And then there is a bunch of pulsars predominantly in binaries, which are at short spin periods and lower spin period derivatives. And then there are high energy emitting pulsars, strongly high energy emitting pulsars, which have been detected. They occupy again a certain preferred regions in this diagram. We will try and see what sense all of these tend to make. So we also see that the large majority of pulsars are detected at radio wavelengths. So more than 2,800 pulsars are known today. And about a couple of hundred are known at higher energies. And most of them have been detected by the Fermi Gamma Ray Telescope. Now, if you look at the total electromagnetic luminosity at each of these different bands, then we find that the electromagnetic luminosity of any pulsar peaks at high energies, not at radio band. Although most of them are observed at radio band, whenever we observe high energy emission along with radio emission, and we can plot the total energy as a function of total energy lost, total luminosity as a function of photon energy, we find that the maximum amount of electromagnetic luminosity is generated at high energies. Here is a high energy emission spectrum of the Crab pulsar. So this is plotted as the total energy radiated in any given band. The horizontal axis is photon energy. So this is 1 million electron volt. this is 1 kilo electron volt. And you can see that the total energy emitted peaks around 100 kilo electron volt, which is in hard X-rays. This is all gamma rays, and you can see that the detectable emission from Crab pulsar exists all the way up to tera electron volt over here. So radio is not plotted here. We'll show the radio in comparison in a later slide. But this is just to show that the total energy that is emitted peaks in around hard X-ray to gamma ray band for Crab pulsar. And for most pulsars where broadband emission have been detected, the high energy emission carries most of the energy. Okay, so electromagnetic radiation in radio and higher energies carries away some of the rotational energy that the pulsar is losing, which is evidenced by its spin down. But there is also another form in which the pulsar loses energy, and that is a large amount of relativistic electron-positron pairs leave the pulsar magnetosphere. They get accelerated by the pulsar, and then they go out from the pulsar magnetosphere into the surroundings. Now, if the surroundings happens to have a confining structure like a supernova remnant, which happens to be the case in Crab nebula, then these particles which come out of the pulsar accumulate inside the nebula. So now let's look at this Hubble telescope optical picture of the Crab nebula. You see these filaments. The filaments are the hot gas which comes from the material that was ejected in the supernova explosion that gave rise to this remnant, and partly from interstellar medium. And this is H alpha emitting excited hot gas. But what you see inside a faint diffuse blue glow here with no such structure is in fact coming from these relativistic particles which have been injected by the pulsar into the cavity. Now, these filamentary structure of hot gas is most evident in optical, a little bit in infrared, but as you go to shorter wavelengths like ultraviolet or X-rays and so on, then these filamentary structures is no longer seen, and you begin to see more and more prominently the interior diffuse emission. For example, this is far ultraviolet and near ultraviolet picture from AstroSat. Here is a picture from Chandra X-ray Observatory. So Chandra X-ray Observatory can see the diffuse emission in the inner bits of it. We can expand this. It looks like this. You have the pulsar here, and there are these rings which are seen. So this is an evidence of a wind that is going out in a toroidal fashion from the pulsar. The pulsar spin axis is like this, right here. And there is also an evidence of some jet-like ejection from the pulsar poles. So the Crab nebula consists of all this. It surrounds the pulsar PSRB 0531 plus 21, which is the Crab pulsar. You have thermal filaments plus non-thermal diffuse emission. There is streaming wind, shocks, knots, jets, all of these things. So all this emission that you're seeing is coming from the wind that is being ejected by from the pulsar, and a significant fraction of the pulsar's rotational energy loss is injected in the form of this wind, which then may radiate after they go out of the pulsar magnetosphere. So if you now look at the total energy budget of the Crab nebula and compare it to the Crab pulsar, so here is the picture which you saw already, these gray points. This was the spectrum of the Crab pulsar itself. Now, The Crab pulsar spectrum at lower energies, including radio, is also shown here. So you can see the total energy emitted in radio is much smaller than the total energy emitted in higher photon energies, that in shorter wavelengths, like X-rays and gamma rays. And the energy emitted by the Crab nebula is much larger than all of this emitted by the pulsar itself. So the net energy budget of the energy lost by the pulsar is the sum of all these things. And when you sum it all up, you will come close to the total rotational energy loss. Some of it will still be there, which is not radiated out in electromagnetism, but remains in the relativistic pair wind. Okay, so now how do we estimate the total energy loss? We know the spin frequency, we know the rate of change of spin frequency. So it is easy to define the rotational energy loss as the moment of inertia times spin frequency times rate of change of Prince frequency. So ddt of half I omega squared. But to put a number to it, although we have the measurement of these two, we need a value for the moment of inertia. To get the value for the moment of inertia, we need to know something about the structure of the star. So now let me digress a little bit into describing in very crude fashion the structure of a neutron star, which acts as a pulsar. So the neutron star, as its name suggests, is largely composed of neutrons, but there is a progression of structure as you go from surface to the interior. The very outer parts of the neutron star have a crust. This crust is made up of regular nuclei, and as you go go inwards, the free neutrons begin to appear. In the outer part of the core, in the outer part of the core, nuclei completely disappear. And you get a sea of free neutrons, protons, electrons, and muons. Then, when you go to the very dense regions near the center of the star, the real composition of that region is actually still unknown, because our knowledge of laboratory physics does not tell us unambiguously what should be the nature of material at such high densities, which are much higher, which at densities much higher than the densities inside the atomic nucleus. So densities here are around the density of the atomic nucleus or just above. And then as you go to inner core, the density rises well above the density inside an atomic nucleus. In the crustal regions, the density is below that inside the atomic nucleus. So a star like that, a neutron star, has a mass, as we have measured, the measured masses of neutron stars lie in the range of about 1.2 to 2 times the mass of the sun. And the typical radius is about 10 kilometers. So you can work out the density of this star, which is extremely high, of the order of 10 to the power of 15 grams per cubic centimeter. Now, because there is a little bit of uncertainty regarding the nature of the inner core, that reflects in the uncertainty in the radius, and hence also in the uncertainty in the moment of inertia. So as a function of mass, one can ask, in accounting for different possibilities, what the moment of inertia could be. And you can see that each of these lines correspond to different assumptions regarding the nature of the interaction and hence the nature of the inner core. So it's somewhere in this range. These are different possibilities about the interior, and this is plotted as a function of mass. So the moment of inertia so lies somewhere around a few times 1 to 2 times 10 to the power of 45 gram square centimeter. So we take moment of inertia of the order of 10 to the power of 45 gram square centimeter, plug it in this, and then you get a rough number about the spin down power. So once we have the spin down power, we can compare it with the total electromagnetic luminosity that we are observing. This is the total electromagnetic luminosity that we are observing in all wave bands put together. And here is the total spin down power. This dashed line would indicate equality. Now, large majority of objects fall below this dashed line. So you can see that the radiative efficiency lies anywhere between close to 1 to less than 10%. There are some cases which happen to lie above it, but you can see that the error bars are such that these could be simply measurement error. So this could probably be well below this line. So the radiative efficiency of most pulsars is somewhat below unity. It's about 10 to 20% in many cases. So rest of it, therefore, goes out as pulsar wind. So now we know the electromagnetic the spin down energy loss. We can put it to some use to estimate some other parameters of the pulsar. Assuming that the pulsar is spinning down like a magnetic dipole. So if you have a magnetic dipole inclined at an angle alpha with respect to the spin axis, and the spin angular frequency is omega, then the rotational energy loss ddt of half pi omega squared in the magnetic dipole model can be equated to 2b squared r to the power of 6 sine squared alpha divided by 3c cubed times omega to the power of 4. So r you get from neutron star models is about 10 kilometers. Omega one is measured. These are constants. Sine squared alpha we don't know to begin with, but we can, it anyway lies between 0 and 1. So we can assume a value. Let's put this to 1 to start with. Then one can invert this equation and one can find an estimate of the magnetic field strength. So it works out to be some constants here and proportional to square root of the spin period times the period derivative, both of which are measured. So once we measure spin period and spin period derivative, we can use these measurements to get a feel for the magnetic field strength of the pulsar. And the ratio of spin period and the period derivative also gives you a characteristic age of the pulsar. So in this period derivative diagram, we can now look at these different quantities, and then we get a feel for these numbers for these neutron stars. Now, let's pay attention to these different colored lines. The green colored lines sloped this way are the lines of constant magnetic field. So here is magnetic field of 10 to the power of 13 Gauss, 10 to the power of 12 Gauss, 10 to the power of 11 Gauss, 10 to the power of 10 Gauss, 10 to the power of 9 Gauss, 10 to the power of 8 Gauss down here. So that tells us that a large majority of these pulsars have magnetic fields around a teragauss at the surface with some dispersion. There are red lines here giving you the spin down energy loss. Then the 38 ergs, 36 ergs, 34 ergs, and so on. And that gives you an estimate of the total spin down energy loss of the bulk of these pulsars, which are around about 10 to the power of 34 to 10 to the power of 33 ergs per second. Remember, the solar luminosity is 2 times 10 to the power of 33 ergs per second. And here are the spin down ages: 1,000 years, 10,000 years, 100,000 years, million years, 10 million years, and so on. So as you can again see, the bulk of the pulsars are between million to a few million years old. The clump of pulsars which are down here is by this token, you can see that they are much lower field, around about 10 to the power 8 Gauss, and spin down age is much larger, over 10 to the power of 9 years, between 10 to the power of 9 to 10 to the power 10 years. So these do form a different population. We will come to this again later. So let's look at some other characteristics of the pulsar emission. If you look at the radio emission, let's take a pulsar like this. This is the total radio intensity within a pulse. This is a short fraction, a small fraction of the pulse period. This is the pulses are very sharp and narrow, so this is just plotted to highlight the range over which the radio emission exists. So this is the total emission. This is the emission in linear polarization. So as you can see, linear polarization could be of a very large fraction of the total emission. So pulsar radio emission tends to be strongly polarized. Linear as well as circular polarization is seen. So this is a very characteristic feature of pulsar emission. And if you take the linear polarization and look at its position angle, the position angle often has this very regular sweep as a function of pulse longitude. So it shows like this S curve. If you plot it in a more evocative manner, so plot the polarization angle at different pulse phases. So you can see this polarization angle turning around as the pulse goes by. That means as the beam sweeps your line of sight. So this can be interpreted as follows. So if you look at the pulsar magnetic pole, if you look down on the pulsar magnetic pole, magnetic fields projected on that plane are going radially out from the magnetic pole. And our line of sight cuts this pattern at some distance from the magnetic pole. That depends on the angle between the view axis and the magnetic axis. And for a part of this traverse, the pulse is on. So this is the duration of the pulse. So this line is solid. This dotted line is the line of sight as it moves along, but there is no emission that we see from those regions. And during this, the polarization does this. And if you map it, you would find that this polarization will fall directly on the projection of the magnetic field lines. So as a part of the linear polarization, the linear polarization position angles are indicating to us what is the projected angle of the magnetic field line at any of the pulse longitudes. So this tells us a lot about what kind of emission mechanism is in place. And curvature radiation was postulated as the main emission mechanism in radio wavelengths based on this observation. We will come to that in a moment. Another important property of radio emission from pulsars is that when you average a large number of pulsars, each pulsar has a very characteristic profile. So if I give you the average profile of the pulsar, and if you have studied many pulsars, by looking at the profile, you should be able to tell which pulsar it is. So it is like a clear, unique signature of that pulsar. But if you look at individual pulses from this pulsar, they show a lot of diversity. They don't all look alike, and they don't fully illuminate this envelope at every pulse. So every single pulse illuminates a little bit of this. So if you look at the train of pulses as shown here, each pulse is different. Some are bigger, some are smaller, and each of them illuminate a part of this profile. When you add it all up over many pulses, then you will see this pattern. And this pattern, as an average pattern, is stable. But single pulses are not like that. So single pulses sum together to give you the average pattern. So that means there is an underlying guiding envelope. All these sub-pulses occur within that guiding envelope. And also what I can see is that from pulse to pulse, there is a drift in the position at which the sub-pulse occurs. So this is indicative of pulses occurring in some sparks in the magnetosphere, and the spark moving around or rotating around in the magnetosphere. So it comes at a different longitude every time the pulsar comes around, and after a while it comes back to the same phase. Okay, so that brings us to a discussion of the pulsar magnetosphere. So let's take a very simple picture of dipole magnet spinning around its magnetic axis. Such a thing would work like a dynamo. So if you put a voltmeter between a pulsar with a 10 to the 12 Gauss magnetic field spinning at 1 second and measure the voltage drop between the pole and the equator, it will work out to be a staggering 10 to the power of 14 volts. So with this kind of voltage drop, there will be a very strong electric field around the neutron star, strong enough to pull out charges from the surface. And these charges will then move around in the magnetosphere and will try to neutralize this strong electric field that is generated due to the spin of the very strong magnet. Now, the charges can move around in the magnetosphere, and they can try to neutralize by distributing themselves and producing an electric field which cancels the electric field due to the rotating magnet. But to stay stable like that, the charges will then have to co-rotate with the neutron star. It is possible for them to co-rotate if they just hang around in the magnetosphere. But if you are co-rotating, as you go further out from the neutron star, the circular speed of rotation, which is omega times r, will keep going up as r goes up. At some point, it will reach the speed of light. So clearly, something which is even outside that will not be able to co-rotate. So this part of the magnetosphere, which has field lines closing within that distance, and that distance is now called the light cylinder distance, is called the closed magnetosphere. And charges residing in that closed magnetosphere can co-rotate, and that part of the magnetosphere can be inert. However, magnetic field lines which do not close within the light cylinder, they cannot co-rotate, and charges on them then therefore will have to move out along the open field line, and as the charges move out, you cannot really neutralize the accelerating potential which is available in this on these field lines entirely. So there are two effects which happens. One is this charges which move out due to these field lines being open, and second effect is that the general relativity causes frame dragging, and the effective angular speed near the star is different from the angular speed further away. So therefore, the meaning of co-rotation itself cannot be entertained on these open field lines. So therefore, you will have a residual accelerating voltage that will appear. Now, this accelerating voltage can accelerate charged particles. The charged particles can radiate. Now, just a quick recap of some basic properties of radiation from accelerated charge. If a charged particle is accelerated with an acceleration a0 in its instantaneous rest frame, and its charge has this is a charge q, then it produces a power which is proportional to square of the charge and square of the acceleration. And the radiation, instantaneous radiation, is polarized. The electric field is proportional to the line of sight unit vector cross the line of sight unit vector minus the velocity vector in units of c cross the acceleration vector in units of c. And when the charge moves, then the radiation gets beamed along the direction of motion. The faster the motion of the charge, the higher is the degree of beaming. The angle within which the radiation gets beamed is about 1 over the Lorentz factor of the charge. So since we will be dealing with highly relativistic charges, we will deal with radiation cones which are extremely narrow. And in a magnetic field, a charge can experience acceleration because of the Lorentz force. So because of the Lorentz force, the charge will gyrate along the magnetic field. This requires some perpendicular momentum with respect to the magnetic field to be present for the charge, and then it will gyrate, and this gyration, because of that acceleration, will produce radiation, and that will take away the perpendicular momentum of the charge. And over time, if all the perpendicular momentum is radiated away, then the charge will start moving along the magnetic field. And this kind of radiation, which is called synchrotron radiation, will exist in the presence of this perpendicular momentum. When it is not there, synchrotron radiation will stop. However, a charge moving along the magnetic field can also radiate if the magnetic field is not straight but happens to have a curvature. Because if any charge has to move along a curved line, then there is a radius of curvature here, and that curvature requires a centripetal acceleration, and that acceleration will cause this charge to radiate, and that is called curvature radiation. So in pulsar magnetosphere, what happens is that synchrotron radiation happens very quickly. Most of the perpendicular momentum gets radiated out immediately, and the charge begins to move parallel to the field line, but the field lines not being straight but having curvature because of the dipole nature will cause the charge to radiate, and that is the curvature radiation which we tend to see at radio wavelengths. Where do these charges come from? As I said, the charges are initially pulled out from the stellar surface because of strong fields, electric fields. Now, once they're pulled out of the stellar surface, they're immediately accelerated in a very high voltage to extremely high energies. Now, as soon as they're accelerated, they'll radiate. They will do synchrotron radiation as well as curvature radiation. And all of this radiation will produce high energy gamma rays. The high energy gamma rays will then interact with the local magnetic field and produce electron-positron pairs. Those electron-positron pairs will again get accelerated in the electric field existing in the open field line region. They will further radiate, further produce gamma rays, which will create further set of pairs. So this will go on for several generations, and pair creation, acceleration, curvature radiation, and again pair creation produces a cascade. It fills the region with charges. And once a large number of charges appear, then the acceleration region will get moderated a little bit. So the amount of accelerating voltage effective acceleration voltage will reduce. It might get reduced significantly, in which case the acceleration will be halted for a little while. But in the open field line, charges will go out. As the charges go out, accelerating voltage will appear again, and you can have this process repeating at some interval. And this large, highly accelerated wind of relativistic pair plasma will leave through the open field lines, and that's what causes the pulsar wind. And these accelerated pairs will also emit electromagnetic radiation that we see. Because that Lorentz factor is extremely high, their emission is practically directed only along the direction of their velocity. And as they move along the field line, the emission gets directed along the field line. And that is why you see the pulsar radiation beams being so narrow and being so closely following the magnetic field cone that emerges from the polar caps. Now, I talked about acceleration region near the polar cap, but if you look at the full magnetospheric solution of a pulsar, this is a numerical simulation of a force-free dipole magnetosphere, then you see there are other regions which can also be extremely active in pair production. And these happen to be at the edge of the closed magnetosphere. These are the closed field lines. So there's a current sheet that appears outside the light cylinder, and inside the light cylinder, it flows along the surface of the closed magnetosphere. So this separatrix, where there is a huge return current, harbors strong accelerating potential, and large number of pairs can be created over here. So this current sheet is highly pair active region. So this current sheet will also be one of the regions of major production of radiation. Now, whatever radiation occurs within the polar cap region, as we said, the gamma rays produced there encounter magnetic field and then produce pairs very easily. So gamma rays cannot get out of the polar cap region very easily. Whereas these regions have much lower magnetic field, and gamma rays produced here will easily get out. So the high energy emission is mostly due to these pair active current sheets. The radio emission may come from closer to the magnetic pole. So that was for an aligned magnet. Now, if you have a inclined magnet, so the spin axis is here, magnetic axis is there, then you can see those regions open up a bit, and you get somewhat more spatial extent of both the current sheet region as well as the polar cap region. And this is what ends up producing all the radiation that we see. Okay, so now we have seen these magnetic fields and the periods that we can measure of these pulsars. And if we plot their distribution in the field period diagram, we find that most of these isolated pulsars are here, and there is a large number of short spin period pulsars with much lower magnetic field. So how do they come about? So let's have a word or two about evolution of pulsars. Most of these pulsars, when they evolve, they start with a certain spin period, and as they lose rotational energy, the spin period will lengthen. So they will move in this direction. And at some point, the spin will become too slow for the pulsar mechanism to operate. So they will die. So the neutron stars will be there, spinning slowly, but will not be acting as pulsars. However, you can see the preponderance of the binaries over here. So if such an object happens to be in a binary system, so at some point, the binary will act in a manner to revive this neutron star and then bring it out here, make it short period low magnetic field object. And this will give it a new lease of life as a pulsar again. And this is called recycling in a binary. And this has two aspects to it. One is reduction of the magnetic field strength, I will not go into the mechanisms of that today, but there are mechanisms that can be driven by binary systems, which can reduce the external dipole field strength. And also, from a long period, the pulsar can be spun up to a short period, and this is easy to understand. So let's say there is a neutron star, and it has a binary companion, which is, let's say, a normal star. The gravity of the neutron star pulls matter from this binary companion. The matter has orbital angular momentum. It sort of spirals down and settles on the neutron star, and it comes to the neutron star. And in the process, it follows an accretion disk. The accretion disk is spinning. Every layer is rotating around the neutron star at the Keplerian period. So as it comes closer and closer to the neutron star, its angular speed goes up. So this matter then interacts with the neutron star magnetic field, and through the magnetic field exerts torque on the neutron star and spins it up. So the closer the matter can approach the neutron star in the accretion disk, the faster the neutron star will get, because the inner orbits have a larger angular speed than the outer orbits. To get close, you need a lower magnetic field, because it is the pressure of the magnetic field that stops this matter from approaching any further. So the lower the magnetic field, the closer it can approach, and higher the accretion rate, the closer it can approach. So the faster spin is achieved for lower magnetic field and higher accretion rate. So the combination of these two can produce these very fast spinning objects like millisecond pulsars. Once the accretion stops, then the spun up pulsar is released from the system, and we can see the fast spinning millisecond pulsars. In the last couple of minutes, I'll just mention the use of pulsars as tools. The pulsars can be used for various things. For example, they can be used to probe the intervening medium. The pulsar signal, as it comes through the intervening medium, the interstellar medium, suffers dispersion, and the quantity of dispersion depends on the electron density in the medium. So dispersion can be used as a probe of electron density, and if you know the electron density, it can be used as an indicator of the distance to the pulsar. So the pulse profiles, instead of being sharp, particularly lower frequencies can look like this fast rise exponential decay, and this kind of exponential broadening happens because the pulsar signal can get scattered, and this scattered signal gives you a longer paths of arrival in addition to the direct path of arrival. So the direct path here and delayed arrival because of scattered path over there, and that gives you a measure of the turbulence in the medium which is causing the scattering. So it can be used as a probe of turbulence as well. And since the pulsar radiation is highly polarized, if you look at the polarization angle as a function of frequency, you can measure the degree of rotation of polarization as the pulsar signal moves through the intervening medium. That gives you a rotation measure, which comes due to Faraday rotation. And this Faraday rotation is a measure of the magnetic field in the medium. So you can use pulsar signals to study these various properties of the intervening medium. If the pulsar happens to be in a binary system, then you can follow the arrival times of pulsars, which is called pulsar timing, and this can be used to accurately track the pulsar's motion in space. And by measuring this motion in space, you can characterize the binary system and measure binary parameters that gives you a precise measurement of the neutron star masses. And with enough measurements, you can even test general relativity. For example, here is the first binary pulsar 1913/16, which has been observed for many years now. And you can see different parameters measured as a function of pulsar mass, companion mass. When you take multiple measurements, the crossing point gives you a very accurate measurement of both the components, the pulsar mass up to large number of significant digits as well as that of companion mass. And using this, you can predict the orbital decay that might happen due to gravitational radiation. And you can actually measure the orbital decay as well. And this follows exactly the prediction of general relativity. So this can act as a test of the general relativity as well. There are other tests of general relativity also possible by using pulsar measurements. The general relativistic effects, the light bending due to general relativity, can be used to measure not just the mass of the pulsar, but also the radius, because the smaller the radius, the larger the light bending, and that affects the pulse profile that we will see from a small hot X-ray emitting spot on the surface. And this experiment is being tried with a dedicated observatory called NISA, which is trying to measure the radius of neutron stars by using this method. Pulsars can also be used for navigation in space. So if you have clocks at various distances, various directions, and you try to measure your timing with respect to that clock, you can fix your distance very. So just like using a GPS, but this is with natural clocks like pulsars. And an experiment that was tried out on board of the International Space Station has been very successful. If you did not use the pulsars and switched off the normal navigation system, its position error started building, whereas if you used pulsars, this position error could be contained very easily. Finally, pulsars are being now positioned to measure the low frequency gravitational wave background that exists in the universe by measuring the minute changes of distance the passage of gravitational wave will cause between the different pulsars and the observatories on Earth. And this is one of the highly awaited measurements using the International Pulsar Timing Array that is going on. So to summarize, I would say that pulsars are among the most exotic objects known in the universe. They have extremely dense matter with as yet unknown properties, strongest known magnetic fields, extreme electric fields, unique radiation properties with very broadband emission, relativistic wind outflows which influence the local environment. They can be used for various measurements like interstellar electron content and magnetic field, masses and radii of neutron stars, used for space navigation as well as detection of gravitational waves. So I'm sure any of you who would like to study pulsars will find this fascinating. Thank you very much.
Thank you, Professor Bhattacharya. It was a very exciting talk, and thanks for covering the entire history of pulsars, starting from the very early discoveries to the very exciting latest developments. So, with that, I will just open the field to questions. If you have questions, you can type or raise the hand. There is one question in the chat box.
Yeah, let me see the chat box. I have to navigate there just a minute. Can you read out the question to me?
Sure. In the plot where you showed the light cylinder for neutron star, there was something called the wind zone. What is it, and what are its constituents?
Yes. So the wind zone is outside the light cylinder. The region is called wind zone because that is where the relativistic electron-positron pairs leave the system and go out from the pulsar's own confinement. So the content, of course, are relativistic electron-positron pairs.
Okay, thank you. Any other questions? Please raise your hand. Okay, there is one more question. Why the age of millisecond pulsars is larger than radio loud pulsars?
Why? Okay. First of all, the age that you see there is basically you can say the age from an estimate of the age from formation. Now, in this case, the age will be counted from the time after the pulsar has been recycled or spun up, right? So recycling sort of reinitialize the lifetime of these pulsars. So now, once you have this low magnetic field, the spin down takes much, much longer. So the pulsar can stay active for a very long time. And even when they have stayed active for a billion years or 10 billion years, you can still see them. Whereas if you take a pulsar over here, then in a few million years, it will spin down to such a long period that it will not be active as a pulsar anymore. So it is because of the small magnetic field of these millisecond pulsars, we can see them as active ones for a very long time, very large ages.
Okay, thank you. Any other questions? Sorry, I'm also checking the YouTube because we are live streaming on YouTube, and I'm just checking that if there are any other questions there. Okay, there is one more. Sir, is there any mass limit for neutron stars as compared to Chandrasekhar mass limit for white dwarfs?
Yes, definitely. There is a mass limit for neutron stars. And that is one of the holy grails of pulsar astronomy now, to find what is the mass limit. Because in case of white dwarfs, we know the property of the matter very well. And we can accurately predict what the mass limit should be. On the other hand, for neutron stars, as I already mentioned to you, we don't know the nature of the matter so well. So the mass limit actually depends on the assumption about the property of the matter. I did have a figure which will give you some glimpse of that. Okay, so you can see in these figures, this is moment of inertia versus mass, and you can see this rise and then it drops. So these are the respective mass limits in the different assumptions about the nature of the interaction at very high density. So you can see that in some equations of state, the mass limit comes on, around 1.8 solar mass, in some cases 2.2 solar mass, in some cases a little higher, some cases a little lower. So if we can actually measure the masses of neutron stars and then see up to what maximum limit they go, they will already tell us something about which of these assumptions regarding the nature of matter is valid, which is not. And if you can measure both mass and radius, that will really be a clincher.
Okay, thank you. There is one more question from Priyanka. Does the orbital motion of neutron stars in a binary have any effect on its period?
Observed period, yes. And that is how you know it is moving. So what you see here is the pulsar moves around. So because of Doppler shift, its period will look like it is longer when it is moving away from you. It will look like it is shorter when it is coming towards you. And it is by timing this that you can actually map out the motion of the pulsar in the orbit. Intrinsically, the pulsar is not accreting or interacting with anything else. The intrinsic change of period is just this rotational energy loss and spin down. There is no other intrinsic effect because of it being binary in binary system. But the apparent period, as you see it, will change because of the Doppler shift.
Okay, thank you, sir. Any other questions? We have probably time for one last one. Okay, there is one question from Karthik. Suppose there are any exoplanets around a neutron star, then how will it sustain the life form on that planet?
How do you know that there is actually a life form at all? There are pulsars for which planetary companions have been inferred. So, however, the conditions seem to be much too extreme for what we think is required for life. So I don't think under those conditions, as we see around pulsars, we can imagine that life can exist. But we also don't know in what all different forms life can occur. So it will be very speculative at this point to say. But the life as we know it will be very hard to sustain around the pulsar.
Okay, there is one more question. We can take it. Any superfluid state present in the inner core of neutron star? That is a question. Is there any superfluid state present in the inner core of neutron star?
Yes. So it is definitely present in the outer core. The neutrons in the outer core form a superfluid. Now, inner core, whether it is superfluid or not, will depend on what makes up the inner core. There is the possibility that there is a state called color flavor locked CFL quark state, which behaves a little like a superfluid, right? So it is a condensate of that kind with some relation between colors and flavors. However, the standard superfluid as we know it, it's unlikely to be present in the core. So it can have condensates of various kinds, but to call that superfluid would be a little bit of a stretch of definition.
Okay, maybe we can take one final question. How does the spin affect the shape of the pulsar?
Yes, so one expects that the pulsar would have an equilibrium figure as expected from the spin. So therefore, if it is spinning very fast, you will have it extended in the equatorial regions, squeezed in the polar regions. So it will be an oblate shape. And as the spin goes down, that means as the angular momentum is reduced, the pulsar shape will have to adjust to the new spin period. And this does happen, but this happens in a sort of jerky fashion. And these are phenomena we call as pulsar glitches. So once in a while, the pulsar will jerk itself and come into a new equilibrium state because the angular velocity has reduced a little bit. So it doesn't continuously follow it. So stresses build up, at some point it just lets go, then adjust to the new shape. So it should overall adjust to the equilibrium shape as dictated by the spin of the pulsar.
Thank you. Thank you, Professor Bhattacharya.
Okay,
Thanks
thank
for
you
that.
all. All right,
Exciting.
sure. All right
There
then.
was one question, but I think I can say it to you later on because I think we are
Yes,
running
it's
out of
time.
time.
Yeah.
Okay. Thank you very
Okay.
much for agreeing to give me a
Sure.
talk.
Bye.
Bye.
I'll stop sharing.
Okay, so the next speaker is Dr. Abhirubdata. Yeah, so Abhirup,
Yeah, hi.
hi. Okay, so you are audible and I can see your video as well. So if you want to put up the slides, we can just try that out.
Yeah. Okay.
Yeah, we can see.
So, great.
Okay.
Okay. All right. Am I audible? Hearing? Are you hearing me fine? Okay.
Yeah,
Great.
everything fine.
Um,
Just let me. Yeah. So, okay, everyone, welcome to the next lecture of this session. So, the next lecture will be given by Dr. Abhirubdata, who is Associate Professor at the Department of Astronomy, Astrophysics, and Space Engineering at IIT Indore. All of you must know Dr. Datta by now because he is also one of the organizers of this very interesting school. Dr. Datta did his PhD from New Mexico Tech at NRAO in USA in 2010. And following that, he has been working on primarily on the study of early universe to age 121 centimeter emission, and he also works intricately in the field of radio astronomy, both instrumentation and observation, uh, in the field of aperture synthesis, galaxy clusters, and large-scale structures. And also alongside, he is looking at the galaxy clusters through X-ray observations as well. His interests also lie in the synergy between study of ionosphere and the radio astronomical observations. With that, I welcome Dr. Datta and leave the field to him. Dr. Datta.
yeah. Thanks, Monamita. So today's topic, which I'm trying to cover, is radio astronomy. It's a vast field. So I think just my attempt will be to just give you a glimpse of what is why are we so much excited about doing radio astronomy, and some major areas which we haven't covered yet in this particular school, and we refer to the particular science cases which get addressed by this kind of this wavelength of study uh, by radio astronomy. Okay, so just to introduce this, it is an entire electromagnetic spectrum. You can see that as the wavelengths get higher and higher, this particular end, if you see my cursor, we are more towards the radio wavelength and then further longer wavelengths. Okay, kind of meter scale and higher than that. If you're going higher in frequency, that means the wavelength is going down because wavelength and frequency are inversely proportional. So beyond some point, so in the top you will see the atmospheric opacity. So our Earth has atmosphere which cuts off certain wavelength of radiation, and so we are fortunate that the radio wavelength, most of the radio wavelength, are actually available to be observed from the ground. So it's actually basically very much available for ground-based observations. And after that, soon after that, if you're going higher and higher in frequency, this opacity increases, and then finally you cannot do the observations in the infrared spectrum from the ground. You have to send the space telescopes, and then finally we have a very limited visibility in the visible wavelength, which we can do. But again, the telescope should be placed at a higher altitude to beat the lower atmosphere, which is the troposphere mainly. And then if you go further higher in frequency, the wavelengths get smaller, and you are basically in the ultraviolet, X-ray, and gamma ray, and those are basically done by the space-based observatories. Okay, so coming down to the longer wavelengths, where the radio astronomy is at, you actually can do it from the ground mostly, and you can observe 24/7. It doesn't really, most of the observations doesn't get much hampered due to the daytime versus nighttime. But there is a particular part of the atmosphere, an ionosphere, the upper atmosphere, which gets ionized due to the solar uh, radiation that causes a bit of an issue. So if you're going further lower and lower in frequency or higher and higher in wavelength, beyond a point, the atmosphere, or the ionosphere mostly, cut you off. So it doesn't allow any any radiation from the outside coming in, and as vice versa, going from something which is beamed out from the Earth to going out beyond the atmosphere. Okay, so unless and until you reach that stage, you are mostly okay to do radio astronomy from the ground. And that stage it varies because of the density of the electron varies across the different magnetic latitudes. And so it is mostly around 10 megahertz or lower, but it can change based on the solar activity. All right. So I think you have, so far in this particular school, you have covered various different wavelengths of observations. I think at least already optical, UV, infrared, and now radio is being covered. I think the gamma ray is going to come up in the last day. So this is a picture, a very famous picture put out by NASA in several different wavelength bands. So you have 408 megahertz, which is radio continuum. It's mainly synchrotron radiation, which I think Professor Bhattacharya was also speaking about before. Then it comes to the atomic hydrogen, which has a spin flip transition in its ground state, and that the rest wavelength is 1420.404 megahertz. And this is how the galaxy looks like at that particular frequency. Then you go further higher in 2.8 gigahertz, which is how it looks like. And finally, infrared, mid-infrared, if you're going down, you're going higher and higher in frequency. Finally, optical, X-ray, and gamma ray. Now, why do we need so many different wavelengths? Because in each different wavelength, you have some astrophysical processes going out, and they are manifesting themselves through the different kind of radiations, which are peaking and coming through at different bands. All right. So if you want to make the complete picture of get a complete information about the particular astrophysical source, your best is to combine multi-wavelength observations, information collected from different kind of wavelengths, and accumulate them, and then try to infer what is actually going on in that particular source in the sky. Here it's a famous picture of Crab Nebula. So in X-ray, it looks like this. In optical, it looks like and then radio finally, and then infrared. So I think if you want to make a combined knowledge about the source itself, the crab, you have to actually combine information collected by observing at different wavelength bands. Okay. I skip that. So as we are looking at different astrophysical objects, we're looking at different scales and different masses. So here is my crude way to, I think, just initiate that. So we're looking at our planet Earth. The radius is 6,000 kilometer, kind of. If you move to the satellite, that is different, at 2,600 kilometer in radius. Move to the nearest star. The radius is about 6.9 10 to the power 5 kilometers. So about 100 times more bigger than the planet Earth. If you look at the solar system, so approximate spatial extent is about 122 AU, where 1 AU is kind of 20 to the power 8 kilometers, roughly. So we are slowly zooming out, and now we're looking at a particular galaxy. The size scale is about 10 to 100 kiloparsec, okay, where 1 kiloparsec is 10 to the power 16 kilometers. So it can vary between 10 to the power 17, 10 to the power 18 kilometers. Now let us zoom back a little bit. We started from Earth, which is roughly 6 10 to the power 3 kilometers. Then to Sun, 6 or 7 10 to the power 5 kilometers. Solar system, roughly 10 to the power 10 kilometers, give or take. And then in the galaxy, it is kind of 10 to the power 6, 17 to 18 kilometers. So as you are moving out, so we are a part of our own galaxy. we are residing in one of the arms, and then we are part of the solar system. So as we zoom out slowly, and look at the grand picture of the universe, the size, the mass, both increases. Okay, so that was galaxy. This is a cluster of galaxy, and here the kind of typical size is about 2 to 10 megaparsec. So roughly 10 to the power 20 kilometers. Okay, so and then finally this famous picture, this is Earth, you zoom out, you get the solar system, then the Milky Way, local groups, local supercluster, and then finally this is the fabric of the universe, kind of a filamentary in nature, but also have kind of like the neural nervous system. There is this synapses. There are kind of nodes which are the overdensity of mass, and those are basically the sites of this galaxy clusters. So, if you want to observe this universe at different, so based on what you want to observe, you need a particular kind of telescope. You want to look into a particular kind of a wavelength because you may be interested in a particular kind of astrophysical phenomena which you want to study. So based on those interests, you have to choose the particular wavelength of observation, the kind of telescope you want to look at, because 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 while you're looking at a particular, say, you want to look into a particular star, you need to have a higher resolving power than if you want to look into a particular galaxy as a whole. Okay, and then if you want to look into different kinds of wavelengths, you may be having different interests in different astronomical phenomena. So based on that, you have to tune your telescope both in size and scale as well as in wavelength. Okay. So one thing which is very interesting to all of us, and studying how the universe was formed and how is it evolving to the current day and age. So, as you know, the universe has started from the Big Bang, and then it was very dense, hot and dense to begin with, and it was so dense, it's optically thick, so nothing can be coming out of that early stages, till it became a little bit colder and optically thin. So the first surface from where we can see the light coming out is this cosmic microwave background, or the surface of last scattering, and it kind of represents the earliest most universe we can actually see. As the universe evolved, we have it became colder, it recombined and remained neutral till the first stars, galaxies, and the black holes turn up, and it reionized the universe. And then finally, those stars, galaxies, and black holes evolved through ages and evolved to our present current day stars, galaxies, and black holes, which we see currently. So we are here, kind of. So if we look back in time, and astronomers have this peculiar scale called redshift. So if we look back, we are at current day, so redshift is 0. If you look back in time, the surface of last scattering is around redshift of 1100, and then the first stars is coming out kind of around redshift 15 to 30, and then finally the complete this neutral nature of the universe ends, and things become more ionized, and that is the end of this reionization, kind of around redshift of 8. So as we want to understand the structure formation history of the universe, we want to probe the early ages of the universe, and where radio astronomy is kind of coming up very useful nowadays. I will come back to that in the later slides. So that's kind of the beginning that why you should do radio astronomy, and one of the science cases which hasn't been touched upon so far in this particular winter school. You have learned about radio galaxies in one of the lectures. Pulsars, it can also be observed in radio wavelengths. Our own galaxy, which there was a lecture where you can study that the stars at a little bit higher frequency in radio. How it all started. So it started from a famous man called Jansky, who discovered cosmic radiostatic. He made a telescope to observe at 20.5 megahertz back in 1932, and he observed a cosmic static which is nothing to do with the Earth, and it should be coming from the outside. The next one to mention, I mean, there's a long list of people who have significantly contributed to this particular branch stream of astronomy. But these two people, if we not mention, it is really not fair. So next one is Gottreber, and he was responsible to map our own galaxy with a 10-meter parabolic reflector dish, which is shown here at the back here of his house. And he studied and he detected non-thermal emission, synchrotron radiation from our own galaxy at 160 megahertz. This was done 6 years after Carl Jansky discovered the static. And there are many more. Sir Martin Ryle, who was responsible for synthesis imaging and other things. That's a whole lot of people who has contributed to this particular field. Now, as we see, again, back to that square one, different wavelengths and different frequencies of the entire electromagnetic spectrum. Now, you can define a particular object called resolution, or resolving, ability to resolve two objects on the sky. So what it is, supposedly, you have a higher resolution. That basically means is that you're able to distinguish between two astrophysical objects spatially. And so if they're spatially very close, you need a higher resolution to be able to resolve them out. If you are spatially very far away, a lower resolution telescope is sufficient. Now, if I want to define what resolution of a telescope is, it simply goes as proportional to the wavelength of the observation over the size of the detector. Now, it comes from definite theory, and there's always the proof behind all this. But for this particular lecture, let us take it as an empirical way. That's what the resolution of a telescope looks like, kind of proportional to. So wavelength over the size of the detector. Okay, so it is well known that if you want to have your resolution or resolving power fixed on the sky, you for shorter wavelengths you need a smaller detector, where for the longer wavelengths you need a larger detector, right? Because to keep this lambda or this wavelength over detector size constant, right? So shorter wavelength meaning higher frequency. So as you're going higher and higher in frequency, smaller dish, smaller resolution, smaller size of the telescope is sufficient. But as you go higher and higher in wavelength, you need a larger and larger size dish to keep that resolution constant or safe. That will be very handy, this particular thing, if you can remember till the end. That will be very handy to explain things. Now, typical antennas which we use. So this radio telescope, this consists of different antennas, right? So there's something called Reciprocity Theorem. So typically what we have learned in dynamics is that if you have alternating current fed to a radiating surface, it radiates out power and in a particular wavelength, which is kind of linked to the size of the antenna itself, the radiating body itself, right? So we start from a simple dipole where the size is proportional to the wavelength of the radiation. Now, using something called reciprocity theorem, the same antenna which is transmitting in a particular way can also receive signal in the similar way. So whatever the response of the antenna is while it is transmitting power, the same antenna will be receiving. The receiving mode will also follow the similar properties. Okay. So by using that in radio astronomy, we basically use the similar antennas which are generally used for transmission. We use it for reception of the signal from the cosmos. Okay. So now there are different kinds of antenna. So if the wavelength is 1 meter or higher, typically the antennas used are dipoles, Yagis, helical antennas, or a combination of them in a kind of an array to increase the diameter. Sorry, increase the dimension of the telescope. Okay, we'll come to that and show you some modern version of this. If the wavelength is less than 1 meter, so you're going higher and higher in frequency, then we use typically reflector antennas where there is a passive reflector, parabolic reflector, and there is a feed in the front, in the focus. And we'll talk about it more because most of the antennas which we're talking about is kind of similar in size and shape. Okay, and if you have approximately 1 meter, then you can use a hybrid. Just a rule of thumb, it's not nothing specific. So let's look at few giant antennas in the world. So we have in 1957 we have this 76-meter Jodrell bank antenna telescope built. This is in right where currently the SK headquarters are. And in 1970, the 64 to 70 meter Parkes in Australia, the telescope was built. Then in 1970s, again 100-meter class telescope in Effelsberg was built right in the lower right corner. In 1970s again, this 300-meter telescope diameter in Arecibo, Puerto Rico was made. This is unfortunately has been currently decommissioned as the primary feed fell off and damaged the dish very badly. And finally, we have this 100-meter telescope in Green Bank, West Virginia, and this is 100-meter in diameter. Remember, the difference between all the other four versus this Arecibo telescope is that all the other four telescopes actually can move, can point at different directions on the sky to track a particular source from the rise to the set. It can track the source and collect radiation. Whereas for Arecibo, it is kind of fixed in the ground, so it can only observe the sources which are transiting across. Of course, there is a little bit of a maneuvering can be done, a little bit of tracking can be done, slightly, but not as flexible as the other telescopes which are shown over here. And of course, I mean that Arecibo was the largest telescope till 2012, when China built this massive telescope, a 500-meter in diameter in Guizhou province, and that is actually fixed on the ground, but it actually has actuators fitted below. This is the artist impression, so I don't have actual picture. And so below there is some actuators which actually can reshape the surface of the telescope. And so based on that, although the total diameter is 500 meters, it actually can reshape itself to give an instantaneous diameter of 300 meters, and actually can do a better tracking of the source across the sky. So depending on where the source is, it can actually reshape and give a dish in different direction. So instantaneous diameter of 300 meters dish can be reformed in any part, and it can point to any part of the sky. So you kind of create a beam which is pointing like this, and it can track the source smoothly. Okay, so it can do a little bit better than Arecibo, but I think still not as as good as the Green Bank telescope or others which can actually point in any direction and track the source very clearly. Now, as we have said, that we have a parabolic reflector. So typically the rays which are coming from far away distance are can be assumed to be plane waves. So they are parallel to each other, the rays, and they hit the surface of the dish and gets reflected and gets received by this feed, which is at the at different places, depends on the nature of the feed location. So, say for GMRT or the Giant Microwave Radio Telescope, which is in Pune, near Pune, is using this prime focus system, where this receiving system is kept at the prime focus of the telescope. So no matter what rays are coming, they will reflect and meet at the converge at the focal point. For Cassegrain focus, there is the Allen telescope, Australia telescope compact array. Where you have this. So at the prime focus, you have the subreflector, and so there is double reflections. One, incoming rays reflect on the surface of the dish, and then for again on the surface of the subreflector, and then the receiver system is kept on the inside the dish, and the system to house the further electronics is kept below. Okay, we come to very large array where it is kind of offset cassette ray. So there is a huge because the wavelength observation with VLA goes from 4 meter to up to a frequency of 50 gigahertz. So there are different systems, receiving systems, and they are kept in variety of positions in the center of the dish. So you need the subreflector to little bit, tilt and point the right receiving system, and so that the rays converge and actually point and get recorded by a particular system, which is the wavelength observation at that particular moment. And there are various more. There is Naismith by OVRO, which is the Owens Valley Radio Observatory. There is the Nobayama Radio Observatory using this beam waveguide system, and then Allen Telescope Array, which is now not in commission, and that uses a dual offset, which is kind of, you assume, like half of the parabolic dish to be here. So the subreflector is at the prime focus, and it kindly reflects back and so it is similar to the Cassegrain focus, but assume only half of the dish exists. The other half was never built. Okay. So to show you the actual pictures, this is GMRT, which is the closest telescope to us. It's about 80 kilometers north of Pune. And this is the Cassegrain focus in one of the dishes, and this is VLA, 25-meter dish. This is how it looks like. This is OVRO, one of the dish, and then this is Nobayama Radio Observatory, and this is kind of close to the one which we will show for the SKA mid. So when I will show, I will refer to this point. Okay, but let us go back to the original definition of resolution. So if you want to keep the resolution fixed and you're observing at larger and larger wavelength, you need a larger and larger dish to actually provide that. Now, at a given point, this becomes very impractical to build a large size dish. Okay, so 300 meter was already a little bit stretching it, and there is one 500 meter now. But those are, and then if you want to really achieve further high resolution, that is clearly impractical to build a telescope of that size, a single telescope. And to find a site to actually house that is also another difficulty. So I think kind of a need also that if you want to go further beyond some resolution limit, I think the where you can resort back is doing interferometry. So it's kind of let me define it very crudely, and then we can come back, go forward, and try to explain how this works. So supposedly you wanted to build a large dish of this diameter given by the background. Instead of making that, you were just trying to fill up that dish by making n number of smaller dishes with a much smaller diameter. Okay, and then what you do is, so in order to fill it up, you can just use much more number of dishes to fill it up. That is one way to do it. Or you also use the Earth's rotation to kind of use the projection of the distances between any two antennas to fill up this something called the aperture plane. Okay, so it's kind of a little bit dense. And it takes a little bit of more number of lecture to explain this, but it is something called radio interferometry, and we use the Earth's rotation to fill up this UV plane much more. Okay, so it is linked to something which the physics students have done in their bachelor's. It's called Young's double slit experiment. So if you want to do an exact comparison, like one dish is like one slit of this experiment. So each pair of antennas measures a different fringe pattern, and the distance between the two slits is given by the baseline, and that determines the pattern you see, right? So in this case, we use an array of antenna, and kind of you have, so each pair of antenna will give a different kind of fringe pattern, and if you superpose all the different fringes, you will try to recover back the object as you see in the sky with a very high resolution. And so the trick is, or the success of this particular exercise is to fill up as many number of with more number of dishes. You get the quality of image which you observe through the spread technique becomes better, and the more the time you give to observe it from the rise to the set of the particular object, the better is your response by the interferometer towards the part of the sky in question, under observation. Sorry, and it involves something called it involves Fourier transforms and deconvolution. But for today's lecture, we're not going deeper into that. We'll just try to show you a particular demonstration, a video animation, and which may give some more insight to the actual process which is happening. So this is a simulation done one of my students, Sheila, and here's a kind of a model. Let it run. I will run it multiple times. So on the top left corner, we are simulating a particular point source, just a compact source in the sky. Okay. In the bottom left, we are showing the more number of antennas being packed into this array. Okay, so it goes from 2, which is minimum requirement because you need to have a baseline to at least 2 antennas, and it goes up to 512 or something like that. So how that response, what is the response in the Fourier plane? Okay, the UV plane is given in this top right corner, and then finally the response of the interferometer, the exact the sky as we see by the interferometer is on the bottom right corner. So this is the input image. It's a simulation. Again, disclaimer is it's a simulation. This is the input image. As you can see the source in the sky, and this is what you see finally through the interferometer. But the interferometer, as you go through the different slices of this movie, actually is changing because the number of elements in the interferometer is changing. Okay, so if you just keep looking at this particular video, you will see the number is going from n equal to 2 to n equal to 512. Okay, and as you go from n equal to 2 to n equal to 512, definitely the recovered image, the constructed image of the sky becomes better and better. Okay. So 2, 4, 5, 6, 7, 8, 9. Actually, if you reach 30, it's kind of number of antennas GMRT has. If you reach 128, it is kind of number of antennas currently MWA paper has. And then 512 is a proposed telescope which is coming up. And so they're all relevant number of elements which are seen over here. Okay, so yeah, so bottom line of that particular animation is that you have more antennas. If you are doing a radio interferometry, you have a clearer picture of the sky. Okay, it's not as simple as that. It is kind of a more complex system, but there are a lot of details which are required, and there are courses, there are schools which are organized for NCRA, for example, by NRAO, virtual schools are organized, and if you're interested, you should attend one of them. If you're interested in doing research in this area, definitely you should contact many of us who are giving lectures in this particular school. So, so from the previous simulation, what we showed, one thing to take away is you have more number of antennas, you get a better picture, clearer picture, or clearer response from the sky. Okay. Now, only disclaimer over here, which I forgot to mention, was that this is related to just one time step and for one particular wavelength. Okay. Typically, if you cannot create a monochromatic receiver, so any receiver you want to bring, there will be a finite bandwidth. Okay, so multiple wavelengths, multiple frequency channels, and so more the number of channels or more wavelengths you observe, the better is the response. Again, the more number of timestamps you observe, the still better it is. So this particular entire simulation uses one timestamp, just instantaneous snapshot, and just one channel or one frequency or one wavelength. Okay. Good. So the list of interferometers which are currently operating, I think I've mentioned most of them. There's still some left out, like Westerbork is left out. Okay. Anyway, we start with the GMRT, the upgraded GMRT, which is upgrade from the legacy GMRT, and total 30 antennas are there, 45 meter in diameter, each of them, and it is observing from variety. It starts from 150 megahertz and goes up to 1.4 gigahertz. This is the particular use we have noted it down. VLA in the USA, it is a parabolic array. It has 27 antennas of 25 meter diameter each. MWA is Murchison Whitefield Array in Australia of 128 total stations. Now, this is a difference, and I will show you in a later slide what is the difference between GMRT VLA versus MWA or even LOFAR. LOFAR is in Netherlands. It's an aperture array, and it has 24 antennas, 24 stations in the core, 14 across Netherlands and 14 across the entire continental Europe. HERA is in South Africa. It's a dish array, 512 number of dishes. Meerkat is South African Pathfinder 2SKA, square kilometer array, and it will consist of 64 number of dishes. And the frequency is 500 megahertz to 1670 megahertz. ASCAP is in Australia. It is consists of 36 antennas. SK low, which is coming up in a decade or so, is SK1 low, sorry. That will be consisting of 500 number of stations. It will be aperture array. So, and the SK1 mid will be in South Africa, which is 200-ish dishes. And then finally, for futuristic way, there are a lot of issues of observing the ground, and one of them is radio frequency interference. So we will touch on that, and also the ionosphere. So there has been studies, variety of studies going on how to observe outside the atmosphere of the Earth, either from the orbiting around the Earth or from the far side of the Moon. And I'm just not mentioning all of the concept studies which are going on, but I kind of collect all of them into one, and there are orbiting ones. There are one concepts where you actually lay down several antennas in the far side of the Moon, and you observe from the pristine location. Now, from the Earth-Moon system, the peculiarity or the specialty is that we never see the far side. So it is always away from us. So we always see the near side of the Moon, and we never see the far side. So no matter what happens, about the relative position of Earth and Moon is such that the far side is always away from us. So if you can create some observatory kind of a thing from the far side, it is free from our Earth's atmosphere and all the interference signals which we are creating because of human civilization. They're all away. We can escape all those nuisance terms if you go to there. But the question is how, when, and what it takes to be there. Okay. And is it absolutely necessary to go there? And we cannot do it from the ground at all. This is a beautiful picture of a very large array telescope in New Mexico. This is a St. Augustine plane. And this is really is a very special interferometer. It has 27 number of dishes. It is in a Y-shaped, like GMRT, and but it is reconfigurable. Okay, so currently what we're looking at is the closest compact array configuration, or the D1, which is the maximum baseline, which is the maximum distance between any two antennas, is about 101.1 kilometer roughly. And as you, so every 3 months, VLA changes its design, its configuration, sorry. So it moves from the most compact one, D, to the little bit larger size, C, then B, then A. As it moves from D to C, the maximum baseline extends from 1.1 to 3.6 kilometers. As it goes from C to B, it goes from 3.6 to 11 kilometers-ish. And if one goes from B to A, the maximum baseline becomes 36 kilometers. In the A array, you will only see 2 or 3 or 4 antennas in this particular field of view. Okay. Here's our closest one, and very special, GMRT, and it's built by Professor Govind Swarup. And it's a very innovative system. It's very low cost and innovative because the GMRT, the highest frequency is 1420 megahertz. So you are looking at wavelengths which are higher than, means about 20 centimeter-ish or larger. So that makes your dish, the requirement on the surface accuracy and the surface, compactness goes down, because you only need to have a spacing of lambda over 20 or lambda over 10. So so that was initiated by Professor Swarup, and he designed this smart system where you have this rope. So it is unlike VLA. This is not compact dish. It is not a solid dish. It is perforated. It's kind of a network of ropes, trusses, and so that's very innovative design, and that makes it cheaper also. And this is the prime focus feed on the top, and this is in just 80 kilometers north of Pune. There are 30 of them, and each of them is 45 meters in diameter. Okay. And finally, the best news which can come to this particular wavelength observation is the square kilometer array. So square kilometer array means the total array will have a 1 square kilometer of collecting area. Okay. So as we said, the resolving power is one of the aspects that we have to follow. That is the ability of any telescope to differentiate between two objects in the sky. It's very essential for a telescope. Second thing is the how much signal can it collect. So as your aperture becomes more larger and larger, you can actually collect more signal. So your sensitivity of observation actually grows. So in that quest, you need more antennas, you need larger baselines, and so on and so forth. So the next design in a breakthrough in radio astronomy is SKA1, where it is split into two different continents. It is so large, cannot be handled by one of them. So it is split into two continents. One is in Australia, and it is going to be going from 50 to 350 megahertz. And the maximum baseline will be 65 kilometers. There will be about 1.3 lakh dipoles in this array. And but if you compare the amount of the most striking thing in this particular view graph is that infograph is that it will produce data which is unprecedented and never been tackled before. So the expected data output from this telescope is about 157 terabytes of data per second. Similarly, if you look at the SK1 mid, which is in South Africa, and that is going from 350 megahertz to 14 gigahertz, 200 number of dishes, and you have total output of the data is about 2 terabytes per second. So it's totally a different regime, although it's a decade from now. Thank God it's a decade from now, because there's a lot of work has to be done to be able to contribute to this kind of extraordinary phenomenon. So the amount of data which is collected right now, which we do, is kind of a few terabytes over a few hours of observations with GMRT or even with VLA. This is kind of a regime change. So more usage of things like machine learning, data sciences has to be applied to able to contribute to this field. So exciting new times. This is the animation of how this mid-array will look once it is built. This is the one from the low. Sorry, this is the same the mid. Sorry, this is the low. So this is the difference between between the previous and the next one. So this is the aperture array. So it's a stacking up different multiple dipoles into an array, into a station. So one of this station actually mimics like a one dish. If you're going to compare the aperture array with the dish array, so one dish is equivalent to one station kind of thing, and within of course, the diameter of the dish will be depending on the diameter of the station, exactly. And so these are much larger stations compared to the dish size on the mid array, and yeah, so there are more number of such stations in SK1. Okay, so one of such science which the telescopes, the radio telescopes are doing currently. So what we showed before is the MWA, the LOFAR, and the SK1 low. One of the prime science goal of these telescopes is and will be to hunt down what actually happened in these cosmic dark ages and cosmic dawn, when the first stars, first galaxies actually showed up, and how this entire epoch of reionization actually proceeded and ended. Okay, is one of the very critical, you know, epoch of our structural formation of the universe, which is still not known to us. So this forms a very important aspect of the science observations from the current telescopes like LOFAR MWA era, as well as the future telescope like SK1 low. Okay. Okay, I skipped this for want of time. Okay. To do this, in order to probe such early epochs of the universe structure formation, what we use is this hyperfine transition line from neutral hydrogen at the ground state, which is the rest frequency, rest wavelength is 21 centimeter, or the rest frequency is 1420.405 megahertz. And if you're expecting to see this from a far and far away universe, which is redshifted, so we can just give it this same radiation will be observed from a redshift of 13 object at 100 megahertz, redshift of 20 object at 70 megahertz. Okay, so if you want to observe it, this same transition line from the epochs which we just discussed, cosmic dawn, cosmic dark ages, so the frequency will be much below than 1420, and it will come between, say, something like 70 megahertz to 200 megahertz. Now, what is the problem with that? First of all, to get an equivalent resolution and sensitivity, you need to have a much bigger array. That's why we're going from like a GMRT to a LOFAR or to MWA, then finally to SK1 low. Also, you need to go from popular sites to a little bit far and far remote sites. Why? Because if you remember this frequency, 70 to 200 megahertz, if you're watching radio, the FM band, like Radio Mirchi or any other music channels, they actually cover this band 87.5 to 110 megahertz. So if you're in a populated area and you want to really do the observation, it is almost impossible to detect it, because the signals will be flooded by the interference from this FM channel. Okay, so you need to go to a remote site to get these observations any meaningful significance. So that's why the sites in Western Australia and South Africa are chosen primarily to do this, because the population density is very, very less. I think it is less than 1 over like 100 kilometer or something like that. Some ridiculous low number. And then you also need to be in the right latitude, magnetic latitude, to not to face the very active ionosphere. And therefore, there are various other considerations also to be made. Okay, so if I just recast the previous slide in a different way, this is the last surface of last scattering. Finally, the signal is coming from this dark edges EOR, and then it is coming through various these nice objects which we have seen through the last few lectures of this winter school. Radio galaxies, pulsars, everything is this in the front, and then our own galaxy, spectacular galaxy, which we have seen through Professor Ray Chaudhury's lecture. And then finally our own atmosphere, Earth's atmosphere, and then coming to the telescope. So if I really want to observe this primordial universe, we have to remove or peel out like an onion skin, one by one, the effect of the ionosphere, effect of the galaxy, and the extragalactic, what we call foreground in this case. So signal of one is a noise of the other. So particular case that you have to remove them to actually detect the signal from the primordial universe. I skip this. I'm running short of time. I go ahead and okay. So as we said that we are interested in doing the cosmology with starting this very early universe using this hyperfine transition line of the hydrogen. We are also interested in knowing this current universe and a little bit distant by doing this all sky surveys by using the similar telescopes. And so this is a list of different surveys which happened at different frequencies and with different sensitivity. So you can see that this is the all sky survey done by GMRT and at a frequency of 150 megahertz, very near to the frequency range which we're talking about, which we need to observe to understand or detect this cosmic ionization. Similarly, this is the all-sky survey done by the MWA, which is a CLIM, and also LOFAR is doing several surveys at this frequency. If you're looking at traditional telescopes like VLA, it has done this NVSS all-sky survey at 1.4 gigahertz, and others. This is 5 gigahertz survey by VLA as well. So what we do is by using this all sky survey, we kind of collect information from different parts of the sky. We not only collect information about the galactic synchrotron radiation, but also about different galaxies who are very bright in the radio wavelengths. This is a map, all sky map made at 45 megahertz. This is also made at 150 megahertz or so. So this is a map made by one of my students at 300 to 500 megahertz by using the GMRT. And you can see if you can, there's a particular radio galaxy over here. There is variety of radio galaxies all across the field. Now, in order to detect faint signals from early universe, you need to do deeper observations. And if you want to do deeper observations, you're also actually creating a knowledge about the current day universe in an unprecedented sensitivity. So that is also useful for others in some sense. So this is a spectacular map at this frequency with a very high dynamic range. And this is one more, which another student, Sheila, has done. Is a Lockman hole, a very famous deep field in radio. And you can also see this. We have zoomed in to few of the radio jets, which is one of the topic covered earlier in one of the lectures, and you can see several of them and quite a huge extent. Spectacular images, and you can study. So for cosmologists, these are all have to be just carefully removed from the data set, and for others, these are basically the signal they're looking at. That's the beauty of this kind of observations, that something which somebody wants to throw away very neatly is actually the source of the entire signal and the interest, scientific interest to study. Another kind of object is galaxy clusters. This is the famous one, Able 85, where you see some kind of diffuse emission, which is kind of radio phoenix. And then this is the cluster, and this is the kind of the view with GMRT again. And I finally come to the last part, which is the atmosphere. So as you know that we've mentioned before also, that all the entire radio sky is seen through the atmosphere of the Earth. We cannot avoid that, as you were mostly observing from the surface of the Earth. So what does it do? So ionosphere by itself is a separate topic, and it's very exciting and how it behaves. It has different kind of effects on different trans-ionospheric signal propagation. So it influences the navigation, satellite communication, our the direct TV, dish TVs, and a variety of others. Okay, for us, I just leave you with this. It's a low-power observation, and it's done a movie of what does ionosphere do to our radio observations. Okay, so just explain a bit. One more minute is that the left-hand side is kind of on a very moderate day of the ionospheric activity is not that high, and you are seeing the image, same field of and same number of sources. The movie is made every 30 seconds. So this is a quieter night where you just see that it is just going through something. Nothing much is happening in the sources, but the same field of view on a little bit turbulent day or active ionosphere. Maybe some solar storm was going on, some other scintillation was happening, whatever it is, and you can see the same field is now going through a lot more, getting more affected by the ionosphere itself. Okay, so that's what typically ionosphere do to this kind of observations, and you have to understand that and remove those effects from your observations to actually get to the actual sky you want to see. So in short, that is the whole challenge, to understand and different composition of of the signals in the sky and how to separate them from the obvious noises or nuisance sounds. Okay, I think we're running out of time. I would stop there and take your questions. Thanks for your attention. Thank you.
Thank you, Dr. Datta, for such a very exciting talk. So, any questions? You can raise your hand or write in the chat. Okay, there is one question. What's the reason behind the Y shape of Valley?
Good one. So I think the Y shape is because as the Earth rotates, you are trying to actually cover or sample more and more of the UV plane. So if you have a Y and you consider the Earth rotation, so you make the locus of the baselines that you're actually feeling that entire thing much better. We have a T before in Mauritius telescope, and I think if you look into the array configuration studies, Y actually gives a little bit more better handle in covering this UV plane better than the T. Again, it depends on where exactly you are on the surface of the Earth. So yeah, it depends on that. Even GMRT is also a Y, but it's a fixed Y with a compact core. Okay, the next one is how is the radio wave received by radio telescope and converted into a picture? Okay. Yeah, I showed that. Okay, let me again come back and show the slide. Okay. Yeah. So if you okay, so the radio signals are observed by individual telescope, and they're recorded as a complex voltage at the end. And then we collect for interferometer. We correlate the complex voltages between any two pairs, and we formed something called visibility. Okay, and in a crude way, a Fourier transform of the visibility will give you some kind of very elementary, rudimentary map of this sky. And then if you do some, further precision operations by doing calibration, deconvolution, which will lead from this kind of an image in the which I'm showing to kind of a perfect radio galaxy image. Okay. Again, this is very good way of trying to answer your question. Anything
Any
else?
other questions?
Hello.
Okay. Oh, sorry. Yeah, Shohini, go ahead.
Yeah, hi.
Sir, what? Yeah, hello, sir. Sir, what redshifts does the escape plan to probe after it is built? Like the maximum redshift?
Yeah, so currently the plan is to go down till 70 megahertz or so. Okay, 50 megahertz actually, but yeah, I mean, give or take 70. 70 is kind of which I showed in my slide is roughly actually to 20. Roughly 20. Okay, and the higher frequency is 350, but that is for something else. So up to redshift 20 in this for the hydrogen line, right? Because it's not essentially so for the hydrogen line we are going till redshift 20.
Okay, sir. And at that redshift, what do we expect to see? Like, do we expect um, a spread of radiation like CMB, or do we expect galaxies, the first galaxies?
Yeah, that's okay. So that is the few slides which I skipped in between. So, okay, this is one of the simulation done by Vikrant Chaudhary and his colleagues. So I think if you look at the redshift trend, this is already okay. At 20, it is 10, it is going down. So basically, as you go to higher and higher redshift, you should expect like lesser and lesser reionization taking place. So if you look into the image of the sky, you should expect something like a very smaller Stromgren spheres, right? H2 regions and or bubbles, whatever we say. They are not should not be overlapping. So as the ionization progresses, those bubbles should grow and then they overlap and turn into like something like this more blue region at later stage, right? So yeah, so if you're looking at the image plane, you should hunt for some hole in the sky as a bubble. But if you can look into power spectrum, and depending on what your model is, you have different kind of shapes depending on the neutral fraction of that particular ratio. So if you're looking at 20, you're mostly into the dark ages. So yeah, it should be the early stages of the rearrangement.
Okay, sir. Thank you.
Next, I will ask Shishu to ask the question.
Yes, thanks for the lecture. And I was wondering what advantage the VLA has in terms of radio observation due to its reconfigurability. I mean, in which situation lower than the maximum baseline is preferred, as we know the maximum baseline corresponds to the best resolution.
Yeah, this is an interesting question because so as I said that the a particular maximum baseline actually determines the resolution of the interferometer, but that's actually a crude way to say because you have to actually look into the distribution of the baseline to see seriously actually assess how much sensitivity you have at a particular resolution, right? Because the more number of baselines you have at a particular resolution, the more sensitive you will be for that particular resolution. So what really does, if you are looking at the same part of the sky, but at using different configurations, you can actually uh, concat them together and then form images with excellent precision because they will be sensitive at different resolutions, almost similarly. So, like as you said, that the baseline, the distance actually changes in a factor of 3 as you go from A to B to C to D, right? 36 kilometer down to 1.1 kilometers. So there's a roughly those many reduction in the baseline. So the same frequency at the same different arrays will change your resolution by factor of 3s effectively, kind of, approximately. So you can have a better sensitive image at different resolutions, and so you can recover more information about such objects, which is not possible with the static ones. But there are disadvantages also. Like you will not get the same sensitivity all throughout the year. You have to wait for another cycle to come back and do it. So those things are there. And again, other thing is that interesting thing is that it doesn't changes overnight. So changing between one configuration to the other is a slow process. So typically one antenna gets moved per day. So as I said, every 3 months the configuration changes. That doesn't mean that today is the last day of the 3 months and tomorrow morning it will be another configuration. It means that when A is going to B, there is a huge overlapping phase of A and B. Okay. So some antennas are here, some antennas are there. So actually, if you want to plan and if you know what scale, so remember that the resolution also leads to some particular angular scale which you're sensitive to, right? So if you know what is your scale of observation, like if you're looking at particular radio galaxies, we know the scales. If you're looking at this diffuse, intergalactic, signal from H1, neutral hydrogen, the angular scale is much wider. So you need more compact array for doing that. Whereas if you're looking at the AGNs, you need as much as resolution as you want. And so that's why the VLA even at the A is not sufficient. If you go to VLBA and then VLBI, and then now even this with Radio Astron, they're planning to do, correlation between some space telescope and on the ground, so that to increase the distances further, the baseline further. Does it answer the?
Okay, thank you, sir.
So Chinmoy,
Yeah.
Shahi, what are some challenges we face while analyzing radio images? Yeah, you could ask my students. This particular operation of deconvolution is not straightforward, and it's an iterative process, and there is quite a bit of, first of all, data editing, removing bad data from good data, how to understand what is good and what is bad. Bad meaning typically to identify things which are actually interfering signals, not actually coming from outside, but produced because of some electronics going bad in one of the antennas or so and so, or some radio frequency interferences recorded by few antennas or several baselines. So understanding what is good data and what is not is one of the challenges. And second thing is doing this deconvolution improperly is another one to begin with. There are several others. As you go to lower and lower in frequency, your primary field of view increases, and more you go, the more signal you get. So those are the challenges. If you're going for wider and wider bandwidth of observations, you have to understand there is a chromaticity of the beam, of the sky in general, which affects this kind of things. And so those are also huge challenges. But it's fun. You get some. Ultimately, you get fantastic images, and so it's a good fun and great learning experience. And if you're excited, I think you should think about the the return of making a good image and learning from it. There will be challenges always. Thanks.
Okay. If there are no other questions, we can wrap up this lecture and then move on to the next one.
Okay, thanks.
Dr. Datta. Hello, Professor Gupta. You are on mute still.
You're right. I was on mute. Now can you hear me?
Yeah.
You.
Yeah. Okay, good. All right. So let me know whenever you want to start. I'm sort of ready.
Would you like to share the slides?
Yes, just give me a minute.
Yeah, sure.
Okay. I think you're seeing the full screen, right? Just 1
Yes.
minute.
Yeah.
Okay.
I see it.
Now you can see that, right?
It's still not full screen, but I
Yes.
think
Just give me a
it's
minute. I know what happens is if I make it full screen, then my entire screen gets taken up. But let me just
yeah,
try
that's true.
that.
That's true.
Okay. Now it's full screen, right?
Yeah, now it's full screen.
It's getting truncated at the bottom a little bit.
I think it's okay.
1 minute.
Yeah, I think it's okay.
Okay, and can you see my cursor on the screen?
It's very
Okay.
visible.
All right, fine.
Okay. Okay. So, with that note, we can start our last lecture of our next speaker, Professor Jashvan Gupta, who is the Center Director of NCRA TIFR. Professor Gupta did his PhD from the University of California, San Diego, and his interests focuses on pulsar searches, timing study of pulsars, the square kilometer array, and studies of the interstellar medium. And of course, he is very much involved in radio astronomy instrumentations. It's an absolute honor and a pleasure to invite Professor Gupta to give a talk on the uh, mega science projects of India in astronomy as a part of this school. With that, I welcome Professor Gupta, and the field is over to you.
Yeah, thank you for the introduction and good afternoon to everybody. It's not clear to me how many people are connected and what is also the background, but I expect it to be somewhat diverse. And so, what I will do is I will also build up a bit of background and introduction. Some of it may be part repetition from what you've already heard in some of the earlier lectures, but I think it just helps to reinforce. And then I'll actually move on and talk in more detail about some of the next generation mega science projects in astronomy that India is involved in. Okay, so in that sense, I will give you a bit of a historical perspective and mostly come around to an Indian perspective on what is there today in terms of multi-wavelength and also multi-messenger astronomy. And then move on from there to talk about the three large mega projects related to optical, radio, and gravitational waves that India is getting involved in. And then we can see where those may lead us to. Okay, and so like I said, I'll just start with some basics. We all know this, that astronomy started at optical wavelengths with naked eyes in the beginning. But when Galileo turned the recently invented telescope to the heavens, it revolutionized astronomy forever. And it's instructive on this path to these large mega projects to just take a perspective on how things have evolved in the optical telescopes from the time of Galileo. So this is the small little telescope that he used, and from there on to a replica of what Newton used and what William Herschel used, and so on, to some of these very large modern radio telescopes which are now in operation, and also this futuristic one, the TMT, which we'll talk more in detail later on, which is yet to come up. An obvious thing that you see here is that for some reason the bigger telescopes are the way to go, and therefore it must be better. And it's instructive for us because when we look at different wavelengths and different parts of the spectrum, to understand why bigger is better. And again, this may be revision for some of you, but there are two main reasons that bigger telescopes are better. A bigger telescope collects more light, and therefore it is more sensitive. It can see more objects in the universe than the one with the smaller aperture. The other one is that the bigger telescopes provide higher magnification, which means that you can distinguish between nearby objects or sources in the sky more clearly than the smaller aperture. And that is technically what is called resolution of the instrument. And it's useful to remember, which again is something that all of you would have encountered, that the sensitivity obviously depends on the size of the aperture, in particular the area, which is goes as the square of the diameter of the aperture. And the resolution depends inversely on the size of the aperture, as lambda, the wavelength of the observation, divided by d. And which means that the larger the aperture you have, the better is the resolution, because that is the angle in the sky that you can resolve at a given wavelength. Right. So these are two concepts which will come back to us as we look at the large telescopes in the different areas. And just to understand them a bit better, just an example of what is meant by improved resolution. So this is the picture of the moon that you may just about see with the naked eye where you can just barely make out any details. But even with the smallest telescopes and then with bigger ones, you can start seeing more detailed structure, which means that you're able to resolve out and distinguish objects which are otherwise nearby and close. And we'll do one more example, which will be important when we go to multiple wavelengths also, is the Andromeda galaxy, which is, I think, perhaps one of the best known galaxies outside our Milky Way. And if you look at the Andromeda galaxy, again, with the naked eye or even with a very small telescope, you would see just a small blur. And as you point bigger and bigger optical telescopes to it, you will start seeing both these effects now. You can see many more fainter sources, whether they are background sources or part of the galaxy. They become much clearer. That means the sensitivity of the bigger telescope is better. And you can now also resolve the structure and start seeing more details of the galaxy as well as of the other objects, be it neighboring objects or foreground objects. And so, this is the illustration of these two concepts of sensitivity and resolution. From there, with that short recap, we'll just move to this point, which again, most of you will be knowing by now, that the light is just one part of the large spectrum of electromagnetic waves, which goes all the way from radio waves of the lowest frequency or the longest wavelength to gamma rays with the shortest frequency and the highest the highest frequency and the shortest wavelengths. And the natural question that is obviously asked is, can the same object be studied at different wavelengths of the electromagnetic spectrum? And we often find that the answer is yes. And do the different wavelengths give us different information about the object? And that's more interesting and useful. And again, generally we find that the answer is yes. And again, you may have seen examples of it already. And the third one, which is also interesting, is can some objects or phenomena be studied only at some wavelengths? That means you don't see them at other wavelengths. And that answer is actually also yes for certain cases. And again, you probably would be aware of such examples. So what this basically drives home the point, and here is an illustration. So we are back to our Andromeda galaxy. This is the image as seen in the visible wavelength, of which I showed a picture earlier. And when you look at this object at different parts of the electromagnetic spectrum, you can see that you see both the fact that it looks different, which means you are learning about different aspects of the galaxy when studied at different wavelengths, and you're getting complementary information, and different parts of it shine more brightly at different wavelengths. Here's just one more example. This is the famous Crab Nebula, seen in radio, infrared, optical X-rays. And again, you can see that it looks can look significantly different, and therefore different aspects of the object can be studied. And that is often what the astronomer does, to synthesize all of this information together and then come up with the best possible physical model of what the object may be, which in this case is actually a pulsar at the center, a neutron star spinning rapidly, and the energetics of that interacting with the supernova that created this object, and producing a bright nebula which is clearly visible. So the question that one asks is what about the other wavelengths? And one of the difficulties that, in addition to the fact in the early days there weren't the corresponding telescopes, which really the crucial part is the detector technology to be able to detect the signals at different wavelengths. The other aspect is that not all parts of our environment around the Earth, that is the atmosphere and the ionosphere of the Earth, not all parts of the electromagnetic spectrum can be seen through that, which means that there's an opacity where some parts of the electromagnetic spectrum are blocked out. And so you can see that there are these two windows, the optical window, where the wavelength can actually reach the surface of the Earth. The opacity is quite low. And then there's this big window here, which lies in the radio part of the spectrum, where the radiation from outside can actually reach us on the surface of the Earth. And so it is therefore not surprising that the next branch of astronomy to grow was radio astronomy, of which you just, I think, had a fairly detailed lecture. And so again, some of the things that I may tell you may appear a bit of repetition, but it's still useful to see that. And I just realized that there's a glitch with my file here. There's supposed to be a picture of a typical radio telescope and how it receives the signals and shows them, but that seems to have got blocked out here. But like I said, this may not be new information for most of you. Just want to emphasize a couple of points. One, that the signals are very weak in radio, and therefore you need to do very special processing in order to get enough sensitivity. You remember the first point, you want to collect enough signal so that the fainter sources become visible. And the other point that causes trouble is that along with this signal comes noise, which comes from the electronics and also from the background, from the sky, from other unwanted man-made transmissions and so on. And one has to then make sure that one can pull out the signal of interest from within the noise. And like I said, I won't go into the details of this, but this leads to the fact that you want to build large dishes so that you can collect enough of this signal to get high sensitivity, which is the same thing as building large optical telescopes. Then in addition, you need to have high quality electronics, which introduces minimum noise into the system so that you minimize the effect of intrinsic noise in the receiver. And then finally, because most of these objects that we study, natural phenomena, transmit over large range of frequencies, then you would like to observe with as large a bandwidth of the observation as possible around the chosen radio frequency of observation. Because the more bandwidth you use, the more signal you will collect from this source, which normally the source strength is measured in watts per square meter per hertz. And so, except for spectral line sources, any of these continuum sources will be radiating over a large range of frequency in hertz. And so, you can improve the sensitivity by doing that. And finally, if you can integrate that signal over a long time, that means keep observing the source for longer and longer duration, then you can increase the sensitivity, because it can be shown that the noise grows differently with integration as compared to the signal. Signal will grow directly linearly to the amount of time that you integrate. The noise RMS grows as the square root of the time that you integrate, and therefore, if you integrate longer, you can then start seeing fainter sources, because the signal grows faster than the noise grows. Okay, so these are all ways in which we try to improve the sensitivity of the observation for a radio telescope, starting by collecting more signal and reducing the noise, and getting the best possible. But as we saw earlier, the sensitivity is only just one part of it. There is also the second part, which is the resolution. And here there is a problem for the lower frequencies, the long wavelength radio waves, because even if you take a large antenna of 100-meter diameter, as shown here for the 100-meter Green Bank telescope, and you're operating, say, for example, at 300 megahertz radio frequency, 1-meter wavelength, the resolution you will get is half a degree, the lambda by d. Okay, and half a degree, as I think all of you will be knowing, 30 arc minutes is the angular size of the moon. So we are back to moon that we saw earlier. So what this means is that if you take a 100-meter size antenna and point it to the moon, you will see an image of the moon which is as blurred as sort of what we see with the naked eye of the moon. You can't get any better resolution. Whereas, as we saw earlier, even with the small optical telescope, you can get resolution which is much higher, of the kind shown on the left. And so there is a problem here which radio astronomy had to overcome. And the simple way to improve that resolution or directivity is to use arrays of antennas. And this is what leads to the need to build radio telescopes as arrays of antennas. And this is important because when we talk about the large projects, we have to see in what direction they are growing as arrays of antennas. And so this is an example of one of the first very successful large arrays of this kind, called the VLA, the Very Large Array in New Mexico in the US. And as you can see, that what has been done now is to replace the concept of one big antenna, which would have covered this entire extent, which is of the order of 25 kilometers, with an array of smaller antennas, but spread out so that they cover this distance. And it was shown that you can combine the signals from these individual antennas and generate an image of the direction in which the antennas are looking, where the resolution of that image is now lambda by ds, where ds is no longer the size of the individual antennas, but it is the largest separation of the antennas within the array. Okay, so this allows the radio astronomers to gain back the resolution which they lost because they're operating at a longer value of lambda, a larger value of lambda, by making arrays of antennas rather than single large antennas. And this is to be kept in mind. And what we'll do is we'll just understand this, because when we talk later about large projects and what India is wanting to do, we need to understand what India has done so far in terms of building these things. And again, you would have heard about the GMRT in the previous lecture or even otherwise. It is one of the largest radio low frequency radio telescope in the world. So as you saw, that radio frequency window is quite large, which is accessible from the ground, from around 30 megahertz to about 300 gigahertz, and no single radio telescope can cover all of that. And the radio telescopes are built to cover different parts of the spectrum, and the GMRT, for example, focuses on the low frequency part of that spectrum, from about 100 to 1450 megahertz. And as I mentioned, it follows this concept of building an array. And so it's an array of 30 antennas, each of them quite large in itself, 45 meters in diameter. And they're spread out over a 30-kilometer region. And this is something that was completely designed and built by our group. And it's a completely indigenous effort to build a large-scale facility in the country. It was conceived in the 1980s and built during the 1990s, and has been operational since 2002 as an international facility. And a lot of the work for this we owe to Professor Govind Swarup, who started the group in the 1960s in India. And recently, in 2018, we completed a major upgrade, which has made this facility more versatile with increased sensitivity, so that it can stay at the top in the global scenario. And so this is just a image of what the array layout looks like. So as you can see, there's a set of antennas in a small cluster, 1 kilometer by 1 kilometer, and the remaining are spread out along this kind of a Y-shaped structure, going out to a maximal radius, which is a bit over 14 kilometers. So when you combine the signals from all these antennas, you're actually synthesizing a telescope whose effective aperture is 28 kilometers or a bit more, as far as the resolution is concerned. And as you can imagine, and this is something important to keep in mind when we go to the next step of what are the large mega projects, any such facility is a complicated piece of engineering, in the sense of the various branches of engineering that need to be very of high quality, whether it is a mechanical or servo, or the RF electronics for the antenna feeds, and RF electronics for the rest of the receiver chain, with the high quality low noise amplifiers and so on. And then optical fiber technology to transport the signal from the antennas to the central station located in the, as much as 15 kilometers away. And then finally, the signal is digitized in the central receiver room, and then there's a lot of digital processing that is done in order to be able to make that image with the high resolution that we talked about, or to look at compact objects like pulsars at high time resolution. And then, of course, the lot of the control, monitor, telemetry subsystem, the actual software for running the whole observatory, and then the software for processing the data and getting the final desired scientific output. And a facility like this, again, is used by people from all over the world. And in GMRT itself is used by astronomers from over 40 countries over the years. And it's highly competitive, the time on the telescope. And you have to apply for the time, and it is then reviewed by a committee. And only the best proposals get time. And typically there are about 50% users from India and about 50% from the rest of the countries in the world. And so, as I said, that the GMRT recently upgraded to have much higher capacity to be able to process as much as 400 megahertz of bandwidth of signal instantaneously, which increases the sensitivity and makes it competitive. But we'll see later what is coming next after that. So we'll get back quickly to the multi-wavelength part. And as we said, these are the two windows. And then you ask, well, how do you study the universe at other wavelengths? And I think, again, all of you will be knowing that the way that's done is to put the detector system, the telescope, up in space, high above the Earth's atmosphere or the ionosphere, with observatories that are launched on satellites. And this, again, you would be hearing about some of these, so I won't talk much in detail. Again, just since we are talking about where India is today and what all India would be investing in the future, it'll take a moment to just talk about the AstroSat, which again I'm sure you'll be hearing more in detail. That this has been one of the major accomplishments by Indian astronomers over the last 10 years, in the sense of both building it and operational since the last 5 years or so, is a multi-wavelength space-based astronomy platform, which has coverage from ultraviolet to various parts of the X-ray spectrum, and is a collaboration between different institutions in the country. It was launched, like I said, about a bit more than 5 years ago now, and it has been working quite well and providing lots of interesting new results, which I'm sure you'll hear about separately. And then the last part of this is that today, when we talk, we are not talking about just multi-wavelength, but what is now called multi-messenger astronomy. And again, you would have heard about this. So it's just again a recap that today we can learn about a lot about the universe, not just from electromagnetic radiation, but also from gravitational waves, as well as neutrinos and cosmic rays. And these are created obviously by different astrophysical processes, and thus they reveal different information about their sources. So, for example, as you would have heard, and I'll talk very briefly about it next, the mergers of black holes and neutron stars coming very close to each other, and phenomena like gamma ray bursts and relativistic jets and so on. And here's just one example of the kind of complementarity of information between the electromagnetic spectrum and the other messengers of astronomy now. And nothing illustrates this better than this event such as the binary neutron star merger, which produces signals in all these different areas, all the way covering neutrinos, gravitational waves, radio waves, gamma rays, light, infrared, and all of this then can be combined to get the best idea of what happened with this. And here is just one example. This was the history-making event that all of you would be knowing about, the first cosmic event observed in gravitational waves, and it was seen in gamma rays as well as in optical, and later in much later in radio, and followed up, and all of that information could be combined by the ground and space-based observatories in order to get the better picture. So in fact, radio waves from this event were seen with the GMRT after many weeks to months, when the injected material interacts with the surrounding medium as the jet travels out, and that produces radio waves, which can then be used to constrain what was the original parent object and its surroundings. Okay, so with that kind of background, we are ready to now look at some of these facilities, and I will start by just showing you this snapshot, which is a collection of some of the next generation facilities, from optical / infrared, such as the GMT, the TMT, and the ELT. In millimeter waves, the ALMA, which is actually already operational now, so it is no longer a futuristic facility. It was built over the last decade and is now operational and producing fantastic results. In the radio waves, square kilometer array, which we'll talk about, and in gamma rays, the Cherenkov telescope array, where there is talk of India wanting to be part of it, but there are not yet very clear plans. And then the gravitational wave detections, the LIGO, where there is a plan to have a setup in the country to observe gravitational waves. So out of these, India is actively engaged in these three projects, and so that these are the ones that we will now look at in more detail. And so we'll start with the optical window, the 30-meter telescope. And so the 30-meter, as you can imagine, refers to the effective aperture that this telescope is offering. And so it is part of this triad of next generation instruments, the GMT, Giant Magellan Telescope, and the EELT, the European effort. This is more effort led out of America, but with partnership with many different countries in the world. But you can see they're all aiming for effective aperture size, which is of the order of a few tens of meters. And so what is interesting when you look at this is the complexity, which is, so this is just a cutaway view of what the final facility will look like. And what you can immediately sort of see is that there is a large, very strong this thing of technology which is needed in order to build these. It will obviously have the latest innovations in precision control, phased array of mirror segments, and that's the other thing. So here, the reflecting surface is obviously made up of smaller mirrors which combine together to give you a 30-meter diameter, and then therefore, when the mirrors point in different directions in the sky, they have to have precise alignment. And for this, there's very sophisticated technology, laser-guided star-assist adaptive optics, which we'll talk briefly about, but we may not be able to go into the full details of it. So this, the heart of this is this segmented mirror with 492 individual hexagonal segments, each 1.44 meters in size. And as I was saying earlier, these have to be precisely aligned so that they can work as a single telescope, 30 meters. And this resolution will be 12 times better than what the Hubble Space Telescope gives. Again, remember, resolution is that ability to resolve objects close by in the sky. And this is certainly going to be a factor of 10 improvement from what the Hubble is able to see. And the very crucial thing about this is the adaptive optics, because as you all know, that the reason why the Hubble telescope is up in space and not on the ground is that there are certain limitations of seeing by an optical telescope because of the effects of the atmosphere, where there can be a loss of the quality of the signal, and in order to compensate this, people have worked out techniques where you can adaptively adjust the optics so that you can try to cancel some of the effects of the blurring that the atmosphere produces. And these again require a technology which can really takes a lot of work to make it happen. But if you do it correctly, this is the kind of improvement that you would get in looking at, say, some object, in this case, the planet Neptune, with adaptive optics and without adaptive optics. And the you can ask what all kinds of science that would be done, and this is one of the things that these large facilities are called mega science facilities, not for no reason, because they actually can do a very wide area of science and can address many interesting and cutting edge topics. And so in the case of the TMT, again, all the way from the birth of the first stars and earliest galaxies to the details of the nature and composition of the universe, studying our own Milky Way, formation of stars and planets, and then as well as objects within our solar system, searching for exoplanets and searching for other signs of life in the universe. And one of the things that always comes to play is when you build something which is 5 to 10 times better than anything that exists before in that particular wavelength, you're likely to find interesting new phenomena and things in the universe which you had not thought about or had not imagined and had not really part of the science goals of the facility. And that is what is called serendipity. And a lot of discoveries in astronomy happened due to serendipitous findings. And the thing that's interesting is, where does India stand vis-a-vis such large projects? And I didn't quite do this, but just like I talked about GMRT, I should have talked a bit about what is the largest current optical facility in the country. And this is close to 4-meter size telescope at Devasthal in the Himalayas, and which is also relatively recent. But we do have that as the one of the frontline facilities, and so from there up to the TMT is still quite a big jump in terms of the what the facility can do, what the technologies are required to make it happen, and and therefore also the kind of finances needed in order to build these things and be part of them, and not to mention the human resources required in order to deliver what we have to build, as well as human resources that who can use the facility and get the best possible science done by the Indian astronomy community. So these are all challenges that all Indian participation in the mega projects are trying to address, is to how to make this big leap. So in terms of whether it's technology, finances, or human capital. But all of these present a great opportunity in order to grow astronomy in the country in leaps and bounds by being part of these large projects. And in the process, the hope is that additional big facilities can be built in the country, learning from the technology that is being developed in the partnership to build such large projects. And so in that context, India has a certain set of tasks that it has taken up in the building of the TMT. And I've listed some of those things that India is looking into. Some have been new for Indian astronomy and Indian technologists in order to do these. And therefore, that has required a certain amount of development of new technology in the country in order to be able to deliver these things. And that has been happening. Some where we understand these but have to deliver them at a much better level than what we have been doing so far. And so there's a mix of all of this, spanning items related to the mirror segments, polishing, and then building these very sensitive controls for the individual mirrors, which would allow the aligning to be done precisely, and related things, and some of the control software for the facility, and so on. It's a part of the Indian contribution. And so I won't go into the details of this, but there's just, again, to just bring home the point that there is a lot of high tech that needs to go into getting these things done and working. And so it's an excellent opportunity for growth of technology in the country. And this is one example of the new facility that has now come up at the Hoskote campus of the Indian Institute of Astrophysics for being able to do some of this polishing of the mirror segments, which will be done in India and supplied to the TMT. So with that, I'll move to the second one, which is the square kilometer array, which is now in the radio frequency domain compared to the TMT, which was in the optical. And just a quick background is in terms of what the SKA is. The final SKA is something which is really ambitious. And one way to look at this is that this is a plot showing the relative sensitivity of radio telescopes built from the very first ones that were built in 1940s to scale which goes to 2020 or actually beyond. And you can see that with time, obviously, sensitivity has improved because these various criteria that we discussed earlier, which is ability to collect more signal and reduce the amount of noise and build more sensitive facilities. And when the GMRT was built early days, it was over here. The upgraded GMRT occupies a higher spot on this chart, both in terms of when it was ready and the sensitivity it is achieving. But as you can see, the SKA is almost off this chart. And the idea is to have 1 square kilometer of collecting area. So that means the total area of all the antennas added together, not the area over which they are spread out, just the total area of the antennas will be 1 square kilometer. Just for comparison, each GMRT antenna is about 1,000 square meters. So 30 of them is about 30,000 square meters. Okay, so that is almost 30 times the collecting area of GMRT in terms of the final aim that the SK wants to build. And for various reasons, those are not going to be large antennas like GMRT. Instead of 45 meters, these are going to be more like 15-meter size antennas. And so in order to have this much area with 15-meter size antennas, you need 3,000 antennas in order to do the job, as compared to 30 antennas of GMRT. So now you can start getting a feel for the scale that we are talking about here. And obviously, these are not spread out over a 30-kilometer region like the GMRT antennas spread out. In the final aim, they may be spread out over 1,000 kilometers distances, covering almost a large part of the continent. But like GMRT, they will be connected in real time with optical fiber. So even if they go out to a few hundreds of kilometers, if not 1,000 kilometers, there will be optical fiber for real time connecting the antennas. And the range of frequency is definitely wider than what the GMRT does. It goes from lower than the GMRT frequency to significantly higher than the GMRT frequency. And this, like I said, it's difficult to make one instrument that can cover this, and so it's actually split into two instruments. The lower frequency part from 70 megahertz to about 300 megahertz to be covered by a facility located in Australia called SKA Low, which again you would have heard about, and the higher frequency part going from about 300 megahertz to as high as they can go up to, say, close to 10 gigahertz, to be located in South Africa. It's called SKA Mid. And these are both regions which are chosen because of the very basic requirement that they be radio quiet regions, far away from man-made noise. That means far away from human habitation, but not so far away that you cannot take the various resources that are needed, whether it is power or water or optical fiber connections or so on, so that you can actually build that facility there. And like I'll show in a minute, the cutting edge science, just like the TMT. And it's so large that it's split into two phases. SK phase 1 is what is currently being talked about, which will expected to be completed by 2026-27, and then later to be expanded to the full SKA. And so this is an example of what the SKA will look like in the two locations. So as I said, in South Africa, the core of the array will be located in the northern part of the country of South Africa, in a semi-desert region called the Karoo. And the phase 1 will have 200 antennas of 15 meter size spread out over 150 kilometers. And this is what an artist concept of the antennas looks like. And in Australia, the core of the array will be located at the edge of the Great Australian Desert, on the western edge, where again it's a semi-desert region where you count human population density as half or 1 person per square kilometer. And here the antenna is actually a bit different because this works at very low frequencies. These are more these kind of dipole antennas, and each station will be a collection of 1,000 such dipoles. So you can think of a station equivalent as one antenna, but it has different properties also. And then there will be an array of such stations, just like you would have an array of dishes or antennas, spanning over 80 kilometers in the phase 1. And the total number of dipole antennas is quite large, but the total number of stations will be around 512 stations or so. And such projects usually are collaborations of a large number of countries, because no single country can afford to build something on this scale in terms of the complexity and the finances by itself. And in the case of the SKA, these are currently the active partner countries, and there are some others who are in the process of joining. In fact, Portugal has now formally joined, and some others will be joining. So we have been part of the project again since the early days, and there will be a global headquarters of the project, which will be located in the UK, from where the entire project will be managed. And again, as just to again drive home the point that the technologies in all of these would be really the cutting edge technologies. And in the, you saw an example in the TMT as to what are the crucial technologies. In the SKA, the crucial technologies are the ones which relate to the designing antennas. And you saw two examples of the two kinds of antennas being talked about for the SKA. And then the low noise electronics, where the receivers will be cooled to low temperature so that the noise is minimized. So there's cryogenic receiver systems that to be built. And then to get the data from all of these, it reaches a total capacity of petabits per second, which so the final SK will have data flow from antennas to the central station, which is more than total internet traffic that flows around the world today. And then in order to handle that data and make sense of it and process it and get the images, you need supercomputing capability of petaflops for doing this. And even after that, the volume of data that you generate will be quite large. You have to archive the data, save it and distribute it to astronomers all over the world so that they can use it. And that itself is still a major problem. So here's an example to get a feel for what the flow is like. You're talking about petabits per second, terabits per second, petaflops, and then still you are still saving data at the rate of 300 petabytes per year in these kind of data centers, which will be distributed all over the world. So we were planning to have one data center in India also to be able to host SKA data, where astronomers from India will get priority access for the projects on which they are working to be able to develop analysis pipelines and work with the data. So this is just an example to illustrate again in terms of size. So you know when you think today, you think Google, Facebook, these are large archives of data, but this is what the SKA data archive would be like in terms of the amount that you would be storing per year by the time the SKA is fully active. So this timeline may not be 2024, maybe a bit later, but you will need that kind of a thing. And so I'll just briefly just talk about the areas that India is participating in. We are in charge of the building the overall monitor and control system for the entire observatory, end-to-end management of the observatory, where we will be the main country along with 4 other partner countries building on this. And we were also leading the design work for this, which was finished about a year and a half ago. And we will also be participating in building some of this electronics, which will combine the signals from all the dipoles that we saw in the SKA low station and give the final output from each station to be sent further for the central processing. So this is again technology where India has some interest and some expertise, and we'll be developing it further. We're also looking at some aspects of the signal processing where we want to extract the final signal. For example, pulsar search processing will be one of the compute-intensive data processing tasks that will be running on the SKA. And we have been contributing to the design of this signal processing system, and we'll be contributing even during the construction phase. And we are also looking to build a small part of the receiver electronics for the SKA mid antenna, again based on our experience and capabilities from building things like GMRT and related facilities. Okay, so with that glimpse of SKA, I move to the third one, which is the LIGO, or LIGO India as it's called. And this now moves to out of the electromagnetic spectrum into the multi-messenger domain, where we are trying to now pick up gravitational waves and study the universe. So again, this is background, which many of you will be knowing, that the Einstein's general theory of relativity predicts that you will have gravitational waves generated when certain kinds of activities happen, specifically disturbance of the space-time metric. And so this is an example of a cartoon of the kind of gravitational wave pattern that you would see if you had two in-spiraling heavy objects like two neutron stars or two black holes or black hole and neutron star. When they coalesce and And these are unique ways of studying these objects in this aspect of the universe. And the the LIGO then is a special technology receiver which then attempts to pick up the very weak traverse of the gravitational wave as it crosses the Earth. And what it does is, again, very in a brief nutshell, that it has these very accurately bounced light laser beams over a long distance, which is of the order of kilometers, of a few kilometer long arm length, and bounce back and measure this, and then detect any small disturbance of the space-time if a gravitational wave passes through. And then you do it in two directions, then you get the full information. And so this is the technique that has been used in the three LIGO detectors that exist today, which have been used for the discoveries that you've been hearing about since 2017. And the so this is an example of the one already there in the US. And the kind of objects that, again, kind of science that you can do is you can ask in what all scenarios do you get strong gravitational waves. So it could be a supernova collapse, where neutron stars or black holes are born. It can be the collision or coalescence of two neutron stars or black holes. It can even be any wobbly rotation of a compact object like a neutron star. So if the object is not fully spherically symmetric, then as it rotates, then there is a varying gravitational potential, and you will get the gravitational waves. Also, what are called primordial gravitational waves created in the early universe during the very early times. And so you can even do cosmological studies using that. So all of these, of course, have somewhat different signatures, and this is what the technology that goes into picking these up. Okay. And so once again here, the thing is that the precision that is required for doing the measurement then requires the technological solutions which are of the extreme. So for example, you need these laser beams to travel in almost pure vacuum, or as best a vacuum as you can make. Okay, and over long volumes, as I showed, of the order of kilometers. So this is something which is quite phenomenal to achieve this kind of low pressure in these long chambers. And so this leads to the kind of technologies which are really novel and high tech. And the design of the lasers themselves is a technological advancement, because you need high power, which with very precision control. And same thing for the mirrors, which reflect and bounce the laser beam back. You can't afford to have any vibration, external disturbance, because then that will give you a corruption of the signal. And so there's a precision with which these mirrors have to be maintained and random motions eliminated, and so on. So the kind of control system that is required for doing all this is, again, quite phenomenal. So what happens in the current situation is that there are two LIGO observatories in the US, and the aim is to have a complementary LIGO facility in India, which would then allow us to be able to uh, combine the signals, or combine the results from all of the three. And the advantage is a better localization of sources in the sky. It's again the question of resolution. Can you see or separate or understand where the source is coming from? Not so much separation, but which patch of the sky it came from. So this is the way it's illustrated. So if you had only the two US detectors and you picked up a burst, you would not be able to localize it within better than this banana-shaped object. But the moment you combine that signal from a detector which detects it in India location also, then the volume over which you have to now search to find the parent object or the source is now much smaller. And so you can think of this effectively as a resolution, though it's more a localization, that you're now able to localize the source much better, simply because you have far away spread detectors whose signals you are combining. So in India, the place where the LIGO will come up is now fixed. It's a place called Hingoli near Nagpur. And this is what the architecture of the site finally, when it will be ready, will look like. And this is some photos from some initial work where the land has been acquired and is being made ready for installation, which hopefully will happen once the final approval of the project is done. And the aim is to have something again within the next 5 to 7 years. So as you can see, all of these projects, whether it is in optical, radio, or in gravitational waves, we're all talking about timescales of the next 5 to 10 years, over which these next generation facilities, which promise to do much better and much more than what is possible, will be up and available and allow us a much better view of the universe, which is illustrated in this cartoon, which shows uh, the universe all the way from Big Bang to today, and the different phases and the different things happening in the universe in those phases. And it also shows which of these mega science facilities will be able to probe which aspect of the universe as one of their sort of key areas. May not be the only area. Like I said, any one of these projects has multiple science goals and targets, and therefore multiple aspects of the universe that they will be able to study. Okay, so I'll stop with that, with just a very high level summary of what I've talked about, and I'm happy to take any questions.
Thank you, Professor Gupta, for such a exciting talk and glimpse into the coming future. So, any questions? You can raise your hand or write in the chat. Uh, any questions? Any questions, anyone?
It looks like most people are quite satisfied, or are rather tired after a long series of lectures.
I guess it's a long day. So, there is one.
So what sort of special instruments do we need to maintain the huge data from SKA? Okay, I'm not sure what you mean by special instruments, but as you saw that there are different aspects of the huge data as it flows through the telescope, the observatory, and which I talked about, which is at that point it is the instruments or facilities that are required are both the high volume optical fiber links to transfer the data from the antennas to the central processing, and then the central processing elements, which are very supercomputing capability things to analyze the data. And then finally, when the final data which is to go to the different locations comes out, then it needs to go to the SKA regional data centers, where it will travel from the two locations in Australia and South Africa over again the undersea optical fiber links that exist around the globe. And so those will be required in order to transfer this the large data. And then finally, when it comes to the final locations where it will be stored in these data centers, then what you need is what a typical data center has, which is basically a very good high-speed data storage facility, whereby you can record large volumes of data on media, whether it be disks or magnetic tapes, and then be able to retrieve it or access it fairly quickly when you need it, and also accompanied by enough computing so that you can then do analysis on the data for the specific science goals that the particular team has in mind. And so all of this obviously has to be maintained. And the thing about any of these is that the aim would be to archive almost pretty much all the data. So a typical telescope like this may have a lifetime of 40 to 50 years. And you would want at some point to say, hey, I want to access the data recorded 30 years ago. And can we do that? So, for example, at the GMRT, we are not that old yet. We are, of the order of sort of 18 years in operations, or a bit more. But we have all the data that is recorded from the beginning. So, if you want to go back and ask, well, this object was observed on the following day with the observatory, what does the data look like? Can I analyze it? And you can then ask for it, and it can be retrieved, and you can then download it to wherever you live and work and be able to analyze it. So that is the kind of thing, except it will be at a much, much bigger scale that in the SK, which will all have to be maintained and operated. So I hope that gives you an answer to what you were asking. You asking how how has the location been chosen for the Indigo project? So I think when you say Indigo, you mean the LIGO India project, right? The gravitational wave project. But your question is valid for any project as to how do you choose the location for such large sensitive facilities. And for the LIGO also, this was true. There were many places in India that they searched. And some of the criteria are very similar to when we were talking about the radio telescopes. That you want to be in a place where man-made disturbances are minimum, and for them the man-made disturbance is not radio noise like our mobile phone transmissions or TV transmissions. For them, the man-made or other disturbances are due to vibrations. So you have to be in a piece of land or area where a natural seismic vibrations are minimum, B, man-made vibrations, so no railway line within so much distance, no major highway within so much distance, and all of that. And the seismic properties of the land is very important. Finally, of course, you must get enough land where you can do this 4 kilometer by 4 kilometer thing where you can build it. And but still, like in everything else, you don't want to be too far away from civilization, because you need the resources, whether it is again power, water, humans to be able to travel there and build it and maintain it. So it is a combination of all that, and then who has got the land who can give that to you. And today, as you know, in India, it's not easy to find land free for uh, most things. And so it is a combination of all that which then finally leads one to the best possible choice. And in this case, it happened to be this location that I talked about, Hingoli, in the eastern Maharashtra.
Any other questions? So can I ask one?
Yeah, sure. Of course you can.
So my question is, a lot of the serendipitous or like unknown things are transient events. So my question is, when we are talking about multi-messenger and multi-wavelength, are we planning some combined follow-up kind of a thing when this actually starts operating, where they kind of operate in conjunction with each other? Because often that's required
Yeah.
for,
Yeah.
let's say, gravitational wave discoveries.
I mean, I generally I would tend to agree with you, but I would not say that all of the serendipitous discoveries are transient events, not
Agree,
necessarily.
agree,
I mean,
agree.
some of the serendipity just comes from the fact that your sensitivity or your resolution is so much better that you can peer much deeper into the universe than you could earlier, and then you uncover new phenomena, things which were not seen before. They need not be transients, but it's true that a lot of the things will come from the transient phenomena, where the ability to catch the faint and the short-lived transients is important. And so there is talk of some talk of how you would coordinate between the different wavelengths, and part of that coordination is to do with the response time of the facility. So you say, well, something went off in the sky and was seen at one wavelength, say typically the higher energies, whether it is say gamma rays or even the gravitational waves, and then the other phenomena at other wavelengths follow a little bit later, and then that little bit later then requires that you design a facility which can easily be reconfigured to go and look in that direction. And so, for example, if you ask what is the limitation in, for example, in a radio antenna, the limitation would be how fast can you steer the antenna and move it into the direction from which this new object has been reported. Okay, and so you say, well, I can't steer it faster than a certain amount. So you say, are you going to miss it? So if you want to beat that, then you say, can I build an antenna which sees all part of the sky most of the time? So the issue of steering is no longer a mechanical steering, and you say, I'll steer it with electronic beams. So that SKLO design that I showed, no, where the antenna is a dipole, the dipole sees a very large part of the sky in one go, as compared to a dish of 15-meter size. And so, but then you want to still know, well, object went off in this part of the sky or that part of the sky which is seen by the dipole. That then is done by electronic processing. So you replaced mechanical movement with electronic processing, which is obviously much faster than mechanical movement, and you can hope to go and look at that direction relatively quickly if something is reported. So there are these aspects which are to some extent being thought about, and to some extent there is the aim that there will be coordinated observations for some of these facilities.
Thank you. Any other question? Okay, since no other questions. Okay.
Okay, that's so your question is just for the benefit of everybody else. Do you see quantum computing as a possible replacement for simulations, processing, etc.? For sure. I mean, quantum computing is on everybody's wish list as the technology that could solve many of the computing problems. The issue that remains with quantum computing is the time scale on which something feasible, which is usable by all of us for normal kind of processing, is available. But sure, if if it is available in the right time frame, then it could really solve a lot of the difficulties that some of these big projects, especially a project like the SKA, where the limitation often would be the ability to handle a large volume of data and to be able to process it. And if the biggest traditionally designed computers find it difficult to do it, then that becomes a bottleneck. And if that can be if those machines can be replaced by quantum computing based machines which are practical and realizable and usable by people like us, then that would be a very good solution to the problem.
Okay. If there are no other questions, then we can thank Professor Gupta and thank all speakers. Okay. There is
Yeah.
one final
Thank you.
question. Okay.
Oh, there is one more? Yes.
Yeah.
Okay. I know that would come up. Yeah. So that's a good question. So to understand that, so again, for the benefit of everybody else, is there the question is there any reason behind the Y-shaped array of radio telescopes, or it can also be of another shape? And actually, I forgot to show you the proposed shape for the SK array. But so this question goes back to this thing that you have to understand in detail how come that with an array of antennas just sparsely filling up that big area, how come you can get a good quality image with that resolution? Because ideally you would have said I should build an antenna which fills that entire area. Okay, you're not doing that, so you're taking a shortcut. And so when you take shortcuts, there will be some inaccuracies in what you achieve, and that is true. So what happens is, the technical question that becomes is, how best can you reconstruct the image from a limited number of antennas that you are placing over that big region for getting the higher resolution? And there is a way in which you can do this, which is a complicated combination of the geometry as well as the direction in the sky that you're looking at and so on. But it turns out that, so if you have n antennas and you have to place them optimally to get the best possible image with the best resolution over some area, then one way of arranging those antennas is a Y-shaped structure. It is one of the optimal configurations which optimizes your result for a fixed number of antennas. And that said, it is not the only optimal configuration. There are other configurations. So the one other one is a spiral kind of a structure. And in fact, the SKA core antennas have gone in for a spiral structure as compared to a Y-shaped structure that you saw for both the VLA and the GMRT. But the basic reason is it's an optimization problem.
Okay, so with that, let's end the session and thank Professor Gupta and thank to all the speakers of the session. So that's the end of day 7. Over to you.
Thank you. Thank you, everybody.
Thank you.
So I'm now leaving the meeting. Is that okay?
Okay, thanks.
Yeah,
We are
yeah,
just
yeah.
closing.
Thanks for joining. Thanks for
Okay. Yeah.
giving
All
your.
right. Bye.
Thank you. Bye bye. Okay, so I think we can close the session. Yeah.
Yeah. I don't have the host for today.